will be a star freelancer. Learn new skills. Set your goals. Increase your skills. Browse over 100 plus videos and ebooks. Jump to starfreelancer.eu.
Welcome. My name is Kirill, and I'm a software engineer who likes to preach the learning environment and to share as much knowledge as I can. And therefore, I'm here to share with you my knowledge on regular expressions. You might have heard a quote that says, if you want to solve a problem and you use regular expressions, then you actually have two problems. And this quote is usually cited by people who do not know regular expressions and how to write them. So hopefully you will never need to cite that quote again after this course. So what to expect from this course? First of all, who you are. You, as a student, do not need any knowledge on regular expressions. We will go through everything you need to write an absolutely fantastic one to solve your issues or really tough tasks. So you don't need any prior knowledge, you don't need any programming knowledge. So basically you just need some desire to learn new things and also desire to get your time back from difficult tasks that take a lot of time. And those tasks I'm talking about are usually text related. So for example, it is my example. It actually happened to me. There was a task that would take like an hour or two to solve. And then after applying a regular expression, that would take just a few seconds, really. Of course, I'm not counting the time you have to spare to write the regular expression itself. But after it is just instant result. And if the task is recurring, you don't need to use 1 hour, 1 hour, 1 hour every time it appears. You can just apply the regular expression you have written before to just save you hours of life. Usually the time I save I use to procrastinate, but maybe you use it in some other way. That is totally fine. And what are we going to do in this course actually? So we are going to learn everything you need about regular expressions. And the course is structured in such a way that each lesson is actually based on a practical example. So, well, as title of the course says, it is a practical course. So it will be based on examples. And also, in the end of each section, there will be some extra examples that we are going to go through. And also a quiz of 15 questions that will range from the easy ones to the most difficult ones you might find in your life. So if you actually pass them all in the first try, then you're doing fantastically. And actually that is my goal. So I hope you do so. Now, also in the end of each section, there will be a cheat sheet. So it will contain maybe some syntax, so you can use it to write your regular expressions, maybe maybe some other information on how to write and how the regular expressions are actually applied. And you might wonder, why do I need a cheat sheet? Won't I learn everything here? And yes, you will learn everything you need here. But nowadays there is so much information in the world that you might just forget something, and that is totally fine. It is absolutely fine. It happens to everybody. The important part here is that you actually know where to find the information you need. So to know where to find it, you actually need to know that it exists, right? And in this case, you will learn regular expressions, and if you don't need cheat sheets, that is awesome, just awesome. And if you need them, that is totally fine also. I sometimes also need them, and totally acceptable. So, and why you actually should go through this course? Well, quite simple. You will be achieving great things. First of all, you will be learning a really important tool that is regular expressions, and that will just save so much time. It is ridiculous. You might not understand it at the moment, but when you start using them, it is just beautiful. You get so much time back. And the only resource you cannot really buy or manage, well, you can manage time, of course, but you cannot buy time, right? And so you need to manage time effectively. And if you save as much time as you can, that is just perfect. So the other thing would be that you're going to be the go-to person for questions related to regular expressions. And people who know regular expressions are actually somewhat elevated in the eyes of other people, because usually people think that regular expressions are tough, and if you know them, you're like some type of divine creature. But it is really not difficult at all. Also, you if you help people, if you apply your knowledge to help people, you actually will feel that happiness of saving a lot of hours of work to your friends, colleagues, whoever you're helping, really. So that's awesome. And finally, maybe it is important for you, maybe not, but if you somewhat automate a difficult task during your job that takes, for example, hours or days to perform, then you actually might get a raise here, right? How awesome is that? So that is really it. Hope you guys enjoy. This course will be very practical once again, and we'll have some jokes, bad ones, good ones. You decide. Have a good one. Hello. Let's have a look at the tools we are going to use in this course. And the real only and main tool we are going to use is this site called regex101.com. And this site has been evolving throughout the years, and it really has so many tools that you can use in order to test to test your regular expressions over some strings, that you really don't need any other tool for that. All right. So let's go through it. First of all, let's start by the left part. You have, well, save and share. You can save your regular expression and then share with your friends or colleagues. But the important part here is flavor. It is a flavor of the regular expression that we're going to use. And there are some options here like PHP, another PHP version, Python, Golang, Java, JavaScript, whatever. What we're going to use to learn in this course is actually the same for all of these flavors. And for any other tool that you might be using to write your regular expression, it doesn't need to be a programming language. So let's just go with the first one. Doesn't really matter much. The next section is function. It has a match, substitution, list, and unit test. And we are going to focus on match, and that means that we want our regular expression to match some part of the string or the whole string. The substitution would be that you want to match and substitute that part of the string by something else. We are not going to use that in this course, but you might find yourself using it quite often outside of the course. And if you want to play with it, just go ahead and do so. I will be very happy. And then the other two we are not going to use at all. Now the most important part of this site, and the part where we're actually going to spend the most time, is this space here. So the regular expression space and the test string space. The regular expression space allows us to write the regular expression that we want to test. And remember, well, I didn't say it before, but remember now, you always want to test your regular expression very well, because you don't want some unexpected results. Okay, so this is very important. For example, if you, getting back here, if you write something like ABC, this is a valid regular expression. As you can see here on the right, there is no match because we have nothing to match here. And if we type something like banana, nothing is matched because there is no ABC in banana. We will look how this matching actually works in the future. Do not worry about it. But now if we write another example like ABC, DFG, and ABC, as you can see, the matches, the ABC, appear in a different color. So cyan and some kind of other blue, it means that our regular expression is actually matching those parts of the string. All right. So now moving ahead, this part here allows us to set options. And we are going to use global and multiline options, and we're not going to use anything else, but you can use it if you want. So what does global mean? Global doesn't return after first match. So this is what is happening in the second example. We do not stop applying our regular expression after we match the first ABC and we go to the second ABC and match it. If we remove the global, as you can see, the second ABC is no longer matched because we stop right here. Let's set it back. Now the multiline. Multiline allows us to use some meta characters of regular expressions that we will learn in the future to delimit the start and end of the line and not just start and end of the whole string. So we can define the start of this line and end of this line in the regular expression. If we remove it, we can no longer do so, right? Now, insensitive is interesting if you want it, but we're not going to use it. It is just insensitive case match, so it doesn't matter if the letter is uppercase or lowercase, and so on and so forth. Some interesting stuff here, but, well, not interesting for us, at the moment at least. Now, let's move to the right. We have an explanation. So this explanation is actually explaining what is happening in this regular expression. So we, at the top, have the regular expression itself. Ignore these slashes. It is just delimiting the regular expression. And then MG are the flags that we applied here in the options. So we apply insensitive, I appears also, okay? Also, the flags are explained here, right? They will always be explained. And then the most important part is actually how and what is being matched by ABC. As you can see, it says that the regular expression ABC matches the characters ABC literally. So we know that ABC is going to match A, B, and C. It is just an explanation of your regular expression, and it is very useful. Now down here, we have the matching information. We have match 1 and match 2. We have two matches because we are using the flag, which is a global flag that doesn't return after first match. All right. And finally, the quick reference is, well, for you, if you want to understand or remind yourself how to write some part of regular expression that will match some character or a bunch of characters. And you can see here, it is like a cheat sheet. It is something similar to what I will be providing to you. And well, you can just go here and have a look at it. Like new line, \n, really quantifiers, 0 or 1, a question mark. See, very cool. This is very useful. Now, the cool part, another one, is if you want to actually see how a regular expression is applied, let me remove this second one, and actually see that it doesn't match anything. Here appears a debugger. So if nothing is matching, you are like, what is going on here? So you can launch it here, or you can launch it here, okay? When you click it, it will show you what is going on at each step, okay? So you can play. If you click here, play, it will be applying this regular expression over this text. And look at the text, look at this position as it moves forward. So let's go. See, it matches A. It never goes to B here. Let's go once again. As you can see, it goes to B, but it never matches B because there is no AB, all right? But it matches A. So it is quite cool to understand what is going on. So let's close it here. Well, that is it. And as I said, we will be focusing on this part here. And do not forget to test your regular expressions very well. See you in the next lesson.
Hello, let's have a look at a simple example and check out how regular expressions are actually applied to a string and how the matching itself occurs. So in our tool, which is Regex101.com site, I wrote a test string here, which is banana man, might be a new superhero, you never know, and then a regular expression that is just a bunch of characters, which is nam, and we want to match basically the substring nam in banana man. Alright, so in this case it appears that there is such a match and it is a nam. Alright, but the most important part is for us to understand how it is actually matched, and for that we can use a regex debugger. I've shown you that there is a way for it to trigger in this match information part. So if we change our regular expression and if there is no match, you can launch the debugger and find out what is happening. But if there is a match, it no longer appears. But it is not a problem, because here on the left, under the tools, there is a regex debugger. And let's use it to understand how our regular expression nam is applied to the test string banana man. So I click on it, and I didn't go in depth in the last video on the debugger, and will do so now, so you can actually use it whenever you want to test your expressions. And as you can see, you cannot really move anywhere using those arrows, right? But there are available keyboard shortcuts, and here you go. The most important one and that we're going to use is seek one step backwards, which is an arrow to the left, and seek one step forward, which is the arrow to the right. And we will be using them today. So what we have here are the steps of the matching procedure. So a regular expression when applied to a string is actually a procedure that takes some number of steps. All right. So in this case, to match our name, we will be using 10 steps as described here. But if your regular expression is quite complex and your string might be also very complex, this number can really grow. As this example is simple, it is just 10. So we need to go through 10 steps to actually finish matching our nam regular expression. Now on the left here we have an information about the matches. And first of all, there is a match 1 found in 10 steps. That is the match we're looking for, the nam. And then match 2 failed in 4 steps, and we will look at that and when it happens. Alright? So it happens after the first match. So let's start. As you can see, the position, so first of all, there are actually positions in the regular expression and the test string. As you can see, the position of the test string is at the character B, while the position of the regular expression is at the character N. And what will happen is that we will be applying this N over each character of the string to try to find another N in the string. So we can find an N here, right? An N here and N here. When we find an N, we will try to find A just after the N. So NA is actually fine because it is nay. And this one also works, but this one, the last N, doesn't work because there is no A behind it, so it will not match. And finally, we will try to do the same with M. So let's have a look. I will be using the arrows, and let's start. So first of all, we'll be trying to match N against B, and it doesn't match because B is not equal to N. So we move ahead. As you can see, our position in the test string actually moved, right? It is, just so you know, the position is between the characters because there are some meta characters in regular expressions that can match something that is not a character. For example, we can match the beginning of the string or the end of the string. And as you can see, we can't really say, unless visually, that it is the beginning or end of the string. That is why we are using the position in the test string between the characters. But in this example, do not worry about it and assume that the position is at the next character after this blue line. Alright, so now we are at A and we try to match against N and we fail, and we move on, we move to the N, and N against N is N. As you can see now, when we matched our N in regular expression, we moved to A because we are going to try to match A just right after the N, while in the text string we kind of save it in memory that we have matched N before, and we save that position, and now we move to A and we try to match A against A, and we do so and it is working fine. And now we do the same for M in regular expression against N in the test string, and it won't match. And now look what will happen. So as you can see, as our matching failed, we actually move back, completely back in our regular expression, and we will try to apply it once again. But where do we start applying it once again? Our previous matching was at the letter N, and it failed. So we just move one ahead. That is as simple as it gets, really. So now we will go to the A, and try to match N against A. It fails. Then try to match N against N, matches. A against A, matches. M against M, matches. And as you can see, there were 10 steps here on the right at the top to actually find the first match, right? But as you can see, there is also 2 letters left in the string here, and we are using a global flag here, so it means try to find as many matches as you can. Do not stop just right after the first match. And this is what actually continues to happen in this match 2 failed in 4 steps. So if we click here, it starts from the beginning, but not completely from the beginning. It starts from the beginning of the regular expression, but in the text string it starts from the position just right after we matched. Because, well, if we found the image, why do we want to do it again, right? So we started here, and, well, as you can see, visually it is obvious that it won't match because this one has 2 letters and this one has 3 letters, but we still use our arrows to see the steps. So let's go. N against A doesn't match, N against N matches, but then A doesn't match because it is the end of the line, and that is it. So that is really how regular expressions are applied. Take care of the positions, take note of them actually, not care, and, well, be careful with them. Also use debugger as many times as you actually want to actually understand what is happening. Alright? Practice, practice, practice. Practice makes perfect. Alright, so see you in the first level, the basic level, and hopefully you will have fun, because I'm sure you will actually. See ya.
In this lesson, we will be looking at 2 new meta characters. The first ones we will learn this course, and they are very important, and it is impressive how many regular expressions I've written that just broke because I wasn't using them. It is exceptional to know them. So let's have a look. And during this course, we will be going through practical examples every time. And let's start by the first one. So imagine you are in a situation that you keep receiving some spam emails from some spammers, and you want to write a tool to help you out with those emails. You want to separate those emails and put them in the spam folder. And what you could do is use regular expressions for that. You also noticed that all of that spam emails start with the company's name, which is Regexers. That might be something that we could use. So you decide to write a regex expression, which is just a word in this case. It's very simple, and it matches your email subject. So, well, this email will go to spam. It is all you wanted, you are doing well, good work. But now imagine that you actually like this company and you applied for that company, and you're expecting to receive an email from that company about your application. And imagine that you actually do receive that, an email with a subject application for regexers feedback. Regexers feedback. Oh no, as you can see, your tool has matched this subject. That would mean that you would probably fail to see what is the feedback. Maybe it is positive. Maybe you're missing on something. So here comes the caret meta character. It defines the beginning of the line. So as we can see, the spammers always start with their rejectors in the start of the line of the subject. So we can use caret to define the start of the line. So it matches the start of the line. It doesn't match any character, it just matches the start of the line. And this way, as you can see, this second email is not matched, so it doesn't go to spam. How awesome is that? Wow, you outplayed spammers. Well done. Now imagine that spammers actually got very smart and hacked your computer. They got your tool and they see this exceptional regular expression written and they know how you avoid their spam. And they decide to write something a little bit more interesting and try to outplay you. So they add important in their subject title, right? Important rejectors company official information. And now your tool doesn't match it. Now you are getting spammed. Of course, you could just add the important to your regex and it would match. But you also notice that the spam always ends with no spam, right? No, not spam. So it is really not obvious that this is a spam because it contains not spam, right? Wow, how unexpected. And note that if you continue doing this, like from the start of the line, something changes and you try to add something new to that, it is a never-ending battle with yourself. You will never succeed. And we will see cases, more complicated examples where this won't work at all. So let's assume that this is not the best approach. It is a fine approach in this case, right? It is a simple one and a fine approach. And let's assume that this is not a good solution. And what we could do is use not spam, which is in the end of the email. And you could also just match by the words, not spam. And wow, success, you got it. But I'm not sure but imagine that some companies actually send out emails, and this is true, which are like this: important, not spam, please read. This is ridiculous, but it happens. And as you can see, this not spam would also match, and this email would go to the spam folder. And it seems quite important, asks you to read even. Wow. Anyways, so in this case, we want to match just this one, right? And we know it ends with not spam. And here comes the $sign, which defines the end of the line. All right. And this way we just match the spam email and we once again outplay the spammers. Now, you should be careful with how you use it. When you're using these meta characters, so the caret and the $sign, you do not want to have anything to the sides of it. So, for example, for the $sign, you do not want to have something here, right? Because it won't match. There is nothing after the end of the line, all right? It could actually match a new line that you can see here, but nothing that other than that, there is nothing you can match, right? Same goes for the caret. On the left, there is nothing you can match, all right? So even if you have a new line here, it won't match, right? Because new line is actually at the top, okay? And that's it for now. It is very important to understand that those two characters will be saving you a lot of time. And please do not forget about them. And let's move on. Let's look at the other meta characters. Have a good one. In this lesson, we will be looking at character classes and follow up with our previous example of the spammers trying to get us with their spam in the email. As you may remember, we had this subject title of the email, Important Regexers Company Official Information, not spam. And we actually managed to match it with our initial regex, which was something like this, if you recall. So the $sign meaning that it was the end of the line. And now the spammers actually got a course in programming and they learned how to write randomized strings. And they tried to apply it to their email subject. So they started by digits. And what they started to do is sending out emails that contained a random digit at the end. So emails like this, right? And they thought we couldn't handle it. I'm not sure why, because we are quite good at it. And let's see how we can manage that. Of course, you could do something like this to match the first one, and then use some magic tricks to match the rest, at which we will be having a look a little bit later. But let's focus on character classes. Character classes are defined by these brackets here, and they define a set of characters that can only match one character. So just one character from that set can be matched. For example, we define 0 to 9 integers here, and as you can see, it matches just one integer. So it matches the 1, 2, 7, 9. Note that it might appear that it matches 7 and 9 at the same time, but it is just this side's helper that shows us that it could match them both. As you can see in the description, it says match 3 and match 4. They are two different matches. So to make sure that we only match the last digit, we add what we already know, the $sign, to define the end of the line. And now we only match 1, 2, and 9. Perfect, we did it. But now spammers continue to unfold their attack and add a random letter, a lowercase letter. It can be absolutely anything, right? And how can we match that? Maybe we can write another character class to match that, right? So we can match A, we can match C, D, E, F, and so on. As you can see, 2 of them already matched, 1A and 9F. But we wouldn't like to write all the letters, right? Who would like that? The expression would become unreadable. So there is a shortcut for that. That is called a range. And we can define the range like this. So a letter, then dash, and then another letter. In this case, it is a range from A lowercase to Z lowercase. So it matches everything in the middle and inclusive A and Z. As you can see, it matches everything here. And now imagine that spammers decided to add a random uppercase letter to that. Oh no, we no longer match that. Unfortunate. But we are learning and we are getting better, and we are defining another character class. This character class will now match any uppercase letter. And using the definition we saw here of the range, we can do the same for uppercase. As you can see, A uppercase to Z uppercase matches all uppercase letters. Perfect. Now, you might think that the range is cool, but why do not we have a range for numbers? And we actually do. So 0-9, 0 to 9 matches any number. Also note that these ranges are not predefined. You do not need to exactly use A to Z. You can use something like F to Z, and this one no longer matches because it doesn't match an A. A is not in the range from F to Z. So it is quite customizable, and you can do whatever you want with that. Now, let's have a look at what happens if we actually do not want to use 3 different ranges every time. Maybe we do not know if the order of letters and digits will be this. So first comes the digit and then a lowercase letter and then an uppercase letter. Maybe there is something like this. Uppercase letter, then a digit and then a lowercase letter, for example. And it is possible to join those 3 classes into one, making it just one. It is allowed to have different ranges in the same class. It is not necessary to have any separation between them, right? So as you can see, it matches just one character because it is, well, just one class. But to match all the 3 randomized characters, we can, for now, there is another way to do so, but for now, we can just do a triple of that meta class, character class, sorry. And this way, we match all we want. Now we can add variations of that. Sorry. So we can add another variation and it will match, right? If we add a letter, it will match. If we add 3 letters, it will match. So it matches anything, any letter, any digit. Great. But now the spammers got a little bit more excited and they decided to not use alphanumerics. How can we do that? How can we match non-alphanumeric characters like equals, plus, quotes, anything else, like slashes, question marks? And we could use another character class. So let me add one more here. And it of course doesn't match any of those. And we could actually define a meta class which contains all the non-alphanumeric characters. But once again, that would make the expression a little bit long and unreadable. So you might recall that from our previous lesson, we learned about the start of the line meta character, caret. And this character has a completely different meaning in a character class. If you write it in the beginning of the character class, it negates everything that goes beyond that caret. So what that means? This last character class will match everything that is not a number, that is not a lowercase letter, that is not an uppercase letter. So that is what we got. We match everything that is not alphanumeric. Perfect. Now, one last thing is that you should be careful that the negation actually matches the new lines too. So let me remove everything here and leave just a non-alphanumeric match. As you can see here, I will zoom in. This negation actually matches the new line. If you see the color difference here, it matches the new line, right? So to not do that, you can add the new line here and negate the match for the new line. As you can see, they are no longer matching. Perfect. And that is all for now. Let's see what we can find out in the next lesson. Have a good one. Last lesson, we had a chance to get introduced to character classes. And this time, let's have a look at what shorthands we can use to also describe those character classes inside the character class itself, or even substitute the character class by that shorthand. So what I mean by a shorthand, it is a string of characters which is shorter than the original string of characters that defines some characters we want to match. So for example, if we have a character class that wants to match all the digits, you can see 5 and 3 in this example is matched. We can use a shorthand to also match that. And for digits, it is actually \D. It matches 5 and 3, matches all the characters that are digits. And it is also nice to know that you can use it outside the character class. So it is not only usable in the character class itself, right? So instead of writing the whole character class, you can just write \D and match all the digits you want. There is also a shorthand for negating those matches, and it is very simple in Regex. You just need to write an uppercase letter. So instead of /d, it is /d, and as you can see, everything here matches, instead the digits 5 and 3. Now, if we consider the character class we use to match everything, so digits and all the letters, we can also substitute this by a shorthand, and that would look like \W. \W defines any character that is considered a alphanumerical or an underscore. So if we add an underscore here, it will also match, right? And once again, if you use an uppercase letter, it matches everything but the alphanumerics here. So matches spaces and also dash. Now for the spaces, there is a very useful shorthand. It is very used not just for spaces themselves, but to match everything that is space related. So it could be a space, a new line, a return, a tab, for example, a vertical tab, just really anything. And it is \S, matches spaces in this case. And if we add a new line, as you can see, it also matches the new line here. And as before, if we use uppercase S, it matches everything but the spaces and the new line, right? Now, what we can do is have a character class that will match all the digits, for example, and also all the spaces. Do not forget that a character class matches only one character at a time. So it can match 5, it can match space, space, 3, space, space, or a new line. This is just an example that can be used and improved further, and we will see what we can do there. Now we had a look at the shorthands and some character classes that we can match and that are very used. And now let's see how we can match absolutely anything, any character. It is just a dot. This is a meta character in this case, and it matches absolutely any character once. All right. Note that you can't, if you define a character class and you use dot there, it doesn't match anything, because we can consider that character classes are some sort of their own regex language and that they have different rules. So outside the brackets, outside the character class, the dot will be a meta character that defines any character, while inside the character class, it is just a dot. So if we add it here, it is a dot. It matches. So we had a look at some of the most important shorthands and how we can use them to match really what we most of the times will want to match. And in the next lesson, we will elaborate even more on how we can use those shorthands, how we can use the character classes, and add some extra on top of that. See you soon. Let's have a look at alternation and the use of parentheses to constrain some parts of the regex, and what happens if we do not use parentheses there. So in this case, we will have an example of names for the street, and sometimes we write, if the street is called first, we can write first street, first lowercase street, then using the digit 1, first street with uppercase s, and first street with lowercase s. And our goal here is to write a regular expression to match all the 4 strings here. So let's have a look at what are the different parts that we can find in those 2 strings, for example. As you can see, the first is the same, and the only difference is the first letter of the second word. It is lowercase or uppercase. And we already know how to match that, right? So using character classes, we can define what we want to match, and in this case it is a lowercase s or an uppercase s. Note that, once again, I will repeat myself, but a character class only matches one character, so it will just match this one, for example in the first string, this one, or this one. So our idea here, our goal is to write some regular expression such that when it comes to this part, the second word, we can use this character class to find the s and follow with the street. So now it matches everything here, right? But we want to match the whole strings. And how can we do it? Of course, let's see how we first match the first words first, and first with the digit. Let's see what are the differences between the word and this representation. As you can see, the end of the word st is the same end of this representation, which is st2, right? So once again, as we did with the street, we can write st, and it will match both st's, this one and those two, those two and those two. Ignore the other ones. And now we need to somehow match the fur or one. And can we use a character class here? I'm not sure, because we only can match one character per character class, right? And in this case, we want to match 3 characters, F, I, and R, or just 1 digit. That doesn't sound very simple here to use character classes, and that's where the alternation comes in. Alternation is basically an OR operator. So you write something and you use alternation, and you write something else, and it will define, hey, match this something or match this something. And this actually allows to not just match one character at a time, but match strings, which is very good. It is an, let's say, an improvement for a character class. And let's see how we can do it. So we want to match fur, and then this represents an OR, and now we want to match OR1. All right. So in this case, we match fur, or we also match 1. Great. So what do you think we could do to match everything? Would it be to add st to our regex space and then use our character class for s and then add street? Let's try that. What will happen? So st space our character class and treat. Strange. It only matched those two. So maybe our alternation doesn't actually understand what we want to do here. And that's actually correct. That is what is happening here, because alternation does everything on the left or everything on the right. And we can actually use parentheses to delimit what alternation will use on the left and on the right. So parentheses, by the way, are other sort of meta characters in regex, and they can be written like this. So if we define the parentheses on the outside of the whole regex, nothing will change, as you can see. It will continue to match only the second and the third, the third and the fourth string. But what we really want is an OR between fur and the digit 1. So let's move the second parenthesis after the 1. Oh, perfect. So this time, this regex reads as, hey, match fur or 1, then match character S, character T, a space, then you can match either lowercase or uppercase s, and then match TREET. Great, that is what we wanted. And you might wonder, why would we use character class here? And that's definitely not required. We can substitute this by an alternation, S or S. So lowercase or uppercase, and it will work too. The character classes are mostly used when you want to match just one character. So you could use this, it is not a problem at all. But a character class is used to match just one character, so you might want to use that instead. While on the other hand, you want to use alternation along with parentheses to match a string or maybe a digit sequence or anything else that is more than one character. All right, we are doing very well. This is a good start for us, and let's see what we can find out in the next lesson. Let's have a look at the summary of the first section and some caveats you will want to apply when you write your regular expression. So we first had a look at the first two meta characters, which is the caret that marks the start of the line and the dollar that marks and matches the end of the line. So anytime you want to write a regular expression that, well, starts with something or ends with something, you should be using those two meta characters. Like, really do not forget about them. They are quite important. And in reality, there are only 3 types of meta characters. And the first one is a character that has a meta character meaning only outside the character class. So for example, parentheses. Parentheses outside the character class can be used to, for example, delimit our alternation. And they do not actually match the parentheses themselves. While inside the character class, they match exactly parentheses. They have no meta character meaning inside the character class. The second character that is the second type of the meta character is a character that has a meta character meaning only inside the character class. So in this case, for example, a dash. A dash inside the character class can represent a range. So if you define something like 0-9 in your character class, that means that any digit will be matched. While outside the character class, the dash actually means exactly the dash. It doesn't have any extraordinary meaning. The third and final type of meta characters is a character that has a meta character meaning both inside and outside the character class, but the meaning is different. That's the interesting part. In this case, for example, is a caret. So as we saw before, outside the character class, it marks the start of the line. While inside the character class, it can be used to negate a character class. So match everything that is not something in the character class. Awesome. So for the fourth point, we have a very important one. You should never forget about it. It is a difference between alternation and a character class. For example, if we have an alternation which is A or B or C, and a character class that is ABC, they will mean the same. They will match only A or B or C. But for a generic use case, that doesn't mean that every time alternation and the character class mean the same, right? Because a character class can actually only match one character at a time, while alternation can match as many characters as you define. So do not forget about that. That is an important difference. And if you're writing a character class and then you expect to actually match some sort of string and that doesn't work, remember this. So for the fifth point, it is about negation in a character class. A negated character class, for example, negated x, doesn't mean match unless there is an x. It means match any character that is not an x. It is a subtle difference, but it is very important. Do not forget about it. The case where we want to match unless there is an x will be seen in a more advanced section. And stay tuned for that. That is an interesting one. Finally, we also learned about shorthands to match large strings of our regular expression. For example, -s matches absolutely any space type, be that space, a tab, a vertical tab, or whatever you want. -S, that means that match any character that is not space related. So it is a negation of -s. It is easy to remember that if we have a shorthand, then we can use a capitalized letter to represent its negation, right? Also, we had a look at the match all the digits or any digit with \d and capitalized D to not match any digit, or better, match everything that is not a digit. And finally, \w, lowercase one, matches all digits and all characters from the alphabet. So it is every alphanumeric and underscore. Do not forget about that. And capitalized W matches anything that is not matched by \w. So use that. You will see how worthy is that when you start writing complex regular expressions. It really shortens your regular expression. So that's it for this introductory section. It was a simple one. I hope you got everything. If not, have a look at the videos again. You will get it. It is what you want. And know that from now on, there will be no games. This is getting serious. We will have a look at some cool stuff like counting elements, which actually brings a lot of power to regular expression. So stay tuned and see you there. Welcome back. In this lesson, we will finally start to look at the quantifiers and the way we can actually count the number of occurrences, sequential occurrences, of some character or a sequence of characters. And let's start with an example here, which are phone numbers from Portugal, which usually contains just 9 digits, USA that contains 10 digits, another one from USA with 10 digits, and Sweden with just 7 digits here. And we would like to match only the Portuguese and USA numbers. So you might see that the difference between them is actually, well, the number of digits in the number itself. And that somehow relates with quantifiers, right? So we want to count the number of occurrences of some character in this case. And to match a number, what we would like to do is to use, for example, a character class. As we talked before, it matches any digit, but we can also use a shorthand for that matches also any digit, \D. But now we want to match just the numbers, Portuguese and USA, that contain 9 or 10 digits. We do not want to match the Sweden number. Of course, we could just replicate D, 9, so 9 Ds, \Ds, and this will match Portuguese number, and then use the OR operator and do the same for USA number, but then your regular expression will become unreadable, really. So a better way for that is to use \D, but then use something to actually quantify the number of times you want the digit to occur. And what that means is that the digit must occur sometimes, but it must be occurrences in a row. So it can be digit and then a letter and then a digit. That doesn't count in this case, right? So what we can use are called ranges, but those ranges are outside the character class. So they actually define the range between the number of occurrences you want to have. And they are defined using those brackets here. And basically here what happens is you define the mean and the max number of occurrences of this expression. Could be a complex expression here, but in this case just a digit. And let's see what happens. So we want to match a number which has 9 or 10 digits. So from 9 to 10 should be working, right? It scans the whole line and looks for a sequence of digits between the length of 9 and 10 and matches those two. So we match Portuguese and USA numbers. What if you want to match just the USA numbers that contain 10 digits? And that is possible. You do not need to define a range here. You can just specify the exact number of occurrences you want. So in this case, by specifying just 10, you tell the regular expression engine to match 10 digits in a row. And if you can do it, then you can match the string completely. That's awesome. And by the way, if you want to match, for example, any number of occurrences between 0 and 10, you would be using this, all right? As you can see, it matches spaces also because it doesn't occur as a D, so no digit is matched. But you cannot use something like this, so without the 0 in the front. Although, if you want to match 9 or more digits, you can use this. So you do not need to specify like 10 or maybe 11 here and just specify the 9 and the comma. It means that match at least 9 digits in a sequence. And as you can see, we match the Portuguese and USA numbers as expected. And that's mostly it. In this case, those are the most simpler ways to define how many occurrences of a character or of a string you want. and it will be later expanded into a more complex example, and we will look at it right in the next lecture. So see you there.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
All right, let's move on with our examples and quantifiers. And let's continue with our example actually, but make it a little bit more difficult. So previously we had a list of numbers, the Portuguese, USA, and Swedish numbers, and we wanted to match them. And now we have new entries here that now contain the country code for Portugal, the country code for USA, and country code for Sweden. And we still want to match the USA and Portuguese numbers only, but we also want to match them in different forms. So in this case, the Portuguese number can be without the country code, and it could be also with the country code. And as we have previously seen, this \D 9, 10, it is a range from 9 to 10, actually matched the initial numbers that we gave, so Portuguese and two of the USA numbers, and it also partially matches the other new numbers for Portugal and USA, but we wanted to match the whole number. And as you might have noticed, the country code is actually optional, and that is what we are going to talk about this lesson. Some items that are optional and that can be included in your matching string or not. So let's start by the Portugal, and let's try to match the second number we have provided, the country code. And we might try to match by +351, for example, but as you can see, there is an issue with the plus sign, and that's totally fine because plus is actually another quantifier. It is a meta character, and we will talk about it in the next lesson. But just so you know, to escape meta characters or to make a meta character match its exact meaning, so in this case match exactly the plus sign, we use backslash on it and it matches exactly plus. And as you can see, it matches +351. And now we could add our initial solution with a space in between, because we have a space here, and it would match the Portuguese number. Cool. Although it doesn't match the initial Portuguese number without the country code. So that's why this part is optional. And to tell your regular expression engine that it is optional, you should be using a question mark. So it is like, it might exist or it might not exist. Whatever, do whatever you want, just match it. So by using a question mark here, we do not actually tell the regular expression engine that the whole +351 is optional. It doesn't understand that. What this question mark means is that the previous expression to that question mark is optional. And in this case, the previous expression is just a 1. All right? And to make the whole +351 optional, we should be using something we already looked at when used alternation. They are parentheses. Parentheses do not only delimit the alternation, but they also define some sub-expression. So they allow us to construct sub-expressions and then apply some meta characters over it. Like in this case, we create a sub-expression of +351 and apply an optional meta character to it. So now it is optional. And now, as you can see, by making it optional, we match the second number with the country code, but we also match the first number, the Portuguese number, but with a space, right? That's not what we actually want. So the space is actually also optional, so we should be adding it here and removing it from here. Now it matches perfectly. So really, the optional part is the country code plus the space, right? So now we also want to match the USA numbers, and we still do match the initial USA numbers because they have 10 digits. And given that the country code, the Portuguese country code part is optional, and then we need to match 9 or 10 digits, they match, right? Because, well, if we don't match the country code, that's totally fine. It was optional, no worries. But we do not match the ones with a USA country code number. So let's add that. And in this case, let's use alternation that we learned before, because we actually have two country codes, the Portuguese and USA one, and we can match or Portuguese or USA country code. So let's use alternation here and define the USA country code with a space here, right? As you can see, we get all the numbers matched. That's awesome. And the Swedish numbers still do not match. That's fantastic. Now, I want you to dive a little bit deeper on the question mark here, on the optional. If you look at the description, it says in the end that it is greedy. So that means that the regular expression engine will try to match the expression it was applied to. So that means, for example, if we have some regular expression like a question mark B, that means that the engine will run through the whole expression and it can match or not A, and that's fine. It just needs to match B. But if it can match A, then it will match A. It will opt to match it. It is greedy. It wants to match everything it can. And by making that lazy, so making the engine actually think, hey, I can match or I cannot match, and both of them are fine, I will opt, if I can, by not matching it. So by adding two question marks, you make it lazy. And as you can see in the description here, it is now lazy. So it is fine. If I can go through the string with just B, that's fine. I am not going to match A. So we will be diving deeper on that one, and the greediness and laziness in different search engines is very important, and we will be looking at that in a quite more advanced lessons in the future. And for now, let's move on with other quantifiers. See you in a bit. Right, welcome back, and let's continue with our numbers example. I just wanted to share with you that I actually forgot to mention last lesson that a question mark that defines an optional item can be written as for example, in this case, A and question mark can be written as A and then defining a matching range of 0, 1. It is the same, right? Because question mark can match or cannot match the expression you provide to it, and it is the same here. And actually, any quantifier that we'll be looking at today and in the next lesson can be expressed as this range here, or maybe not exactly this one, but using the ranges. So now let's move on. And in this lesson, we will be having a look at a quantifier that means one or more items or one or more expressions occurrences. And let's see, I altered a little bit our example. I removed the country codes and we now have the original Portuguese number and then just the number without Portugal before it. And I did the same for the USA numbers and the Swedish number. And we continue to want to match just the Portuguese and the USA numbers. And as we already know, by using this expression here, we match any USA or Portuguese number, but we do not want to match the second line, this line, and this line. We want to make sure that there is the country defined prior the number itself. And what we can do is, of course, write something like a simple alternation, really, Portugal or USA, and then a number. And in this case, it will match anything we wanted. But in reality, if you have many more countries, you do not want to keep on writing them. That's not really what you want, right? And the most important part is that there is something before the space in the number itself. There is some sequence of letters, and we can use that to define our regular expression. And as we have seen before, we can use a class, a character class, to define a letter, any letter, but we want a sequence of letters. So lowercase and then capitalized. But we want a sequence of letters here, not just one character. And to do so, we can use the plus sign here. We talked about it last lesson, where I described that it is actually a meta character, and it is actually what it is used for. So by having a plus sign after an expression, we mean that, hey engine, match this expression at least once. So it is actually the same as having one or more times using the range quantifier, but it is shorter to use just the plus sign, right? And if we actually use what we learned before, we can use a shorthand for alphanumerics. And in this case, we will be matching of at least one alphanumeric and then a sequence of digits from 9 to 10. But this also will match something like, for example, this here. For example, the code prefix, but without the plus sign, and it will still match, and that is not what we want. So be careful. W doesn't mean only letters, it also means numbers and underscore. So let's move back to what we had before. So this way we can match the country name spaced and then the number for that country. Awesome. Next, we will be looking at the last quantifier, the most powerful of them all. So, see you there. Welcome back, and let's continue with our example about the numbers. As you might have seen that we actually gave almost no love to the Swedish number, and that will be changed this lesson. And we have another problem. We can imagine that we have a file that is a CSV file, for example, and it has 3 columns: the country, a number, and a description, for example, of that number. In this case, it has 9 digits. Nice description. And we only want to match the second column of the line in all of the lines. And let's assume that the numbers can be from, well, the column could be empty, but it could also contain any number of digits there for the number. So imagine that we have another country here that contains this number with a description desk, for example, and a country 2 that just contains 1 digit with some other description. And our regular expression should not just match Portuguese and USA numbers now, but also the Swedish, the country 1 number and country 2 number. There could also be errors in the CSV, and we want to know about them. And let's see that the country 3 contains no number there, right? Somehow that happens, or maybe there are still no number registered for that country in your application. That could be possible. So let's see how we can do that. What we have used before, so a range from 9 to 10 for the digits, doesn't work anymore because it only matches the Portuguese and USA number, and it partially matches the country 1 number, but we actually don't want that. We want the whole match. to be able to extract that information. And the Swedish number, once again, doesn't receive any love. And also, one of the corner cases is that country 3 with no number also doesn't match anything here. And we should be able to know that it doesn't contain anything. It should match. So what we could do is, well, we know that we want to match at least 0 digits, right? So country 3 has 0 digits, then country 2 has 1, then country 1 has a lot of digits, and so on. So we could use our range here, and it will actually match some different stuff. For example, Portugal will be matching the number, but also some part of the description, and we do not want that. So let's delimit our number by space, and also before the number comes the space. So now everything is matched. That was easy, right? All right, so, but why we are here, right? The meta character I want to introduce to you is actually an asterisk, or you can call it a star. That is actually the same as what we have used before, a range from 0 to infinity. And the star will greedily match, and do not forget that greedy is not always good. It will try to match as many things as it can, and it will match 0 or more things. So the number which does not exist for country 3 will also be matched. And this large number here for country 1 will also get matched. You might, if you have seen a little bit more complex examples for regular expression, you might have seen an expression which contains this sub-expression, a dot and then asterisk. This means match anything and as many times as you want. So it could be match nothing or match absolutely everything. As you can see here, it matches the whole string, everything. Do not forget that the dot is a meta character and it matches any character, okay? So you will probably be using this expression quite often, but do not overuse it. It is very powerful, and I would suggest to use it only in edge cases when you actually know that you do not care what you actually match there, right? You just want to match something. So be careful with that. All right, so the next few lessons will be examples. As we had here some of the examples, the ones we will be having in the next lessons will be a little bit more complex, and we will be trying to unite all the information we got until now on the quantifiers and use some information we got in meta characters and character classes. So stay tuned for that. It will be awesome. See you. Hello. Let's have a look at greediness against laziness for quantifiers. And by default, a quantifier, be that a star, be that a plus, be that a question mark or a range, is greedy. So any quantifier, if you don't denote that it should be lazy, it will be greedy. And what does greedy mean? Greedy means that it will try to capture as many characters as it can, and giving up if necessary for other matches. And lazy means that you actually want to stop. So the quantifier will actually stop if what comes after the quantifier, the next regular expression, actually can match. So the quantifier will not capture as much as they want or as they can, but will stop with the minimum match it can to proceed. And let's have a look at practical examples for that. We have here a, well, really simple text, hello. And let's have a look how different quantifiers behave in a greedy or lazy situation. So imagine that we have a regular expression like dot, an asterisk or a star, that means match any characters between 0 or any other number of time, greedy, and then an L. So we actually can stop here and discuss what we see here. And as you can see, hell is matched with double L, and that is expected. So the quantifier actually matches H, E, L, L, and then it looks for if the next L can be matched, and it cannot be matched against O. So it drops one L, the quantifier drops it, and tries again, and now L can be matched for the second one, right? So the quantifier actually goes until it can no longer. And if we apply laziness, and laziness can be applied using a question mark, as you can see, something changed here, right? And in this case, what happens is that the quantifier is lazy and it doesn't want to match as many things as it can. It is lazy. Come on, I match as few things as possible. I don't want any more. So what it does, the dot matches H, then it looks whether, before the dot matches H, it actually doesn't want to match anything. So it looks whether L can be matched against H, and it cannot. So dot matches that. Then it looks whether L can be matched against E, and it cannot. So dot is matched against that. And then it checks whether L can be matched against the first L, and it can. So the quantifier is no longer applied and L is matched. And as you can see, using laziness actually matches only hell with one L. And if we use a greedy approach, we match the hell with double L, right? So now let's have a look at an optional quantifier, which is a question mark. And let's have an example like, let's start by hell with one L and then add a question mark. As you can see, it is greedy and it can match 0 or 1s, the letter L, and it opts by matching it once. But if we add another question mark, we make it lazy, so it doesn't want to match L. So it opts by not matching it at all, and it works fine. The regular expression applies and it matches just the he. Right? That is cool one. So be careful with laziness and greediness. What about a plus sign? That means one or more are matched. Let's have a look. So help and plus. Once again, it matches HE, then L, and as it is greedy, it matches L at least once and as many times as it can, so it matches it twice. But making it lazy doesn't do so anymore. It goes for the lowest possible amount of matches, and it is 1 for the plus sign, because it is 1 or more, and it just matches the first L. What about the ranges? Ranges can also be lazy, but they, as other quantifiers, are not lazy by default. They are greedy. So, for example, hell and the L can appear from 1 to 2 times. As you can see, the greediness takes place and it matches double L. Now, if we make it lazy, it matches just once, right? And look at that. What do I do? What will happen if I add a O at the end? Will this quantifier actually match? Because if I add an O, it doesn't match against L, right? So it shouldn't be matching because the quantifier is lazy, it opts by matching just once, right? But look at that. It matches everything. So even though the quantifier is lazy, it will match as many things as necessary for the regular expression to actually pass, all right? So it is not like, wow, I'm lazy, I'm not doing anything. No, not at all. It is, I'm lazy, I will do as less as I can. I really don't want to do much, but if necessary, I will, all right? And a greedy quantifier wants to say that I will do as much work as I can, as I want, until I break something and I need to give up some part of the text to match against the regular expression that comes after me. Okay, so this is it. Use it wisely and see you in the next lesson. Welcome. Let's have a look at capturing groups and back references. What is that? We already learned about parentheses and some usage for quantifiers. And for our capturing groups, we're also going to use parentheses. So as you might have noticed, parentheses can be used in many places and can have different meaning for each of the place. So the capturing group, what it means is that you will capture some part of the text. So for example, in this case, we have a very cool sentence. You can capture some part of it by applying a regular expression, and then in the future, you can back reference that capture to try to match the same part of the sentence. So imagine that we capture using a regular expression the first cool, and then in the future, we also want to match another cool here. So we use back reference for that. But of course, an example can explain it better. And let's assume that you have been writing a book, a very long book, and sometimes some errors cripple in your text. And one of the, I would say, most common errors would be a duplication of some word. So in this case, we have a duplication of the word cool. And well, it doesn't make sense to have double cool here, right? Even if the sentence is really cool, it doesn't make sense to have it doubled here. So what we want is to develop some regular expression and then use it in maybe some other tool to substitute these occurrences, and instead of them, write just one word. So it would be just one cool instead of two cools. So first of all, we need to match those words. And in our simple example, it would be as easy as doing so, right? But what if you have something like the town, for example? You have double the, right? It no longer matches. So you might consider using what we have learned so far, like \W to define any alphanumeric, and then using a plus sign to match any kind of word in your text, and then using space, and then doing the same for assuming that it will match cool and the. But as you can see, it doesn't match only the duplicated words. It also matches a and very. And that is, well, expected because you're trying to match just one word, then just really any word, then a space, and then any other word. It doesn't necessarily need to be the same as the first one, right? So this is expected. And we do not want that. We want this second word to be the same as the first one. So what we can do instead, let me remove it, is, let's think about it. We want to match a word. So \W plus matches any word. Nice. Now, as I said, we use parentheses to capture some part of the text in the regular expression. And so we can use parentheses here. And really nothing changed. You continue to match just the words, but now we have the ability to actually back reference what we have matched here. And what we can do now is match a space. And to back reference what we matched before, we need to use backslash and then the number of the capturing group. And the numbering of capturing groups goes from the first open parenthesis to the last open parenthesis. So in this case, this is just the first capturing group. And if we had another parenthesis here, this second one would be the second capturing group. But we will have a look at that a little bit ahead. So we only have one capturing group, so we can't really, for example, back reference the second one because it is just the first one. And if we do with the first one, everything works. So really back referencing is backslash and the number of the capturing group you want to back reference. Now, let's focus on the first sentence here, the cool, and let's see how we can use the numbering of the capturing groups. So assume that we want to match cool. This is just one capturing group, but now let's add an extra pair of parentheses here. And with this extra pair, we actually create another capturing group, right? So nothing really changed in our matching, cool space cool is still matched. But now imagine that I add another cool here. And how can I match 3 cools now? So the first capturing group, as you can see, is cool space cool, while the second one is just cool. So what you want to do is to match another space, and you want to match just one cool. And for that, you can do \2, because it is the second opening parenthesis, and it defines the second capturing group, right? While if you add another cool, you could use the same, right? Space and \2. But you could also use \1, because the first capturing group is actually capturing the cool space cool. All right. So this is basically what capturing groups and back references are, and they are really important for our regular expressions, and they're very useful. You do not want to guess what word will come in the future, and you just capture the one you want it to be and just reuse that. So that's it for now. See you in the future lessons.
Welcome back. And as previously planned, let's work over an example, a little bit more complex one, and write a more generic regular expression to match some cool stuff. And we will be using a lot of material that we have learned so far, not just the capturing groups or quantifiers or whatever we have learned so far, right? So, but let's focus on the example we have seen in the previous lesson. It is duplicated words. Let me just remove this one. And the idea would be, once again, to go through your text. You're writing a book, go through your text and just match and find all duplicated words. They can be separated by a lot of spaces. They could be separated by just one space, by 2, by 3, whatever. And we have here 4 examples. We need to match all of those. The first one is a very cool, with a lot of spaces, cool sentence. The next one is the town was empty. The third is what a time to be alive. So this one has double duplicate. And the last one, this is a nice course, hopefully. And let's write our regular expression for that. We already know that we want to match words. They can consist of numbers. That is not a problem for us. And we want to match duplicate words, actually. And they can be separated by spaces. And all of those occurrences should be matched, right? Cool, the, time, is, bb. So let's see how we can do that. Well, what we have seen before is that we can use \w plus to match any word, and then use the matching group, the capturing group, sorry, then any amount of spaces, and then a reference to the capturing group we have seen, right? And now, not all of them are matching, as you can see. And first, let's go example by example. Cool is matching correctly. The town was empty doesn't match because it is not the same, right? The third one matches correctly. It matches time and bb. It doesn't matter what number of spaces we have, at least one. And the fourth one matches, but it matches incorrectly. What the hell, right? So it matches the part of the this, which is a fine word, but we want it to match is and this one. So to is. Then we need to trim a little bit our regular expression to match those cases. And we can start by this example here, and how we can do that. So we've talked about some shorthands already. The most important ones, like we are using here \w, \s. And there is one that is \b, and \b defines the word boundary. So it means from this point a word starts. And a word is actually what we are defining here. it is described by \w plus, and we can use that in our advantage. So what we want to match actually is a word that starts. We do not want to match part of the word, like in this case. And then we want to match any number of spaces, and then a word that ends, starts and ends, right? And let's see how we can apply that. So, as we decided, a word boundary defines where the word starts, so we can write it here, right? And where the word ends. We could write it here, and as you can see, it would match nonetheless, but it doesn't really make sense to have it there, because having \s already says we want at least one space, so it kinda has a border between the word and the spaces, right? We do not need to say the word finishes here, because a space being there already means the word has finished. And the same happens with the start of the second word. We do not need to define \b here, the start of the word, because the word itself already means that it is starting, right? But we need to define that it actually ends, because let's see at the fourth example. For example, we have this. This is a, right? Those words is and isa are different, but it will still match. So we need to define that it actually ends there. So now it doesn't match, right? But if we remove it, the word ends and everything is fine. Now for the town was empty. As you might notice, the real difference is the uppercase or lowercase letter here for the word, and it can be changed. There are configurations of your regular expression, right? And if you are using a programming language, probably you will be passed the configuration into your regular expression, and usually the configuration is just some sort of letter in some specific space of the regular expression that says match globally or match just once per string or any really other configuration. And let's see what we have here in our tool. Oh, sorry about that. I had to resize it. So in our tool, we can click here. As you can see, it says set regex options, and I have global and multi-line turned on. So global means do not return after first match, so it means it will match as many occurrences as possible in a string, and multi-line means that it will match multiple lines, just like we have here, just for the sake of the example, but you can obviously use it in your regular expressions. Also, as you can see, this is a case-insensitive match. This is what we actually want, but there are also other options, like ungreedy, really cool. It makes quantifiers lazy. Nice, but we already saw how we can make lazy the quantifiers lazy with a question mark, an extra one. And there are also other stuff we can use here. Based on the language you will be using, or tool, not necessarily language, those flags or those regex options might vary, and some tools may have more options, other less, right? But those three are usually will usually appear in any tool. So let's use in case-insensitive match, and as you can see, it immediately applied. And here you can see the options we have. So that's what I was talking about. You might need to write some letter to define the option you want to apply in your tool or programming language. And that is it. So we are matching duplicates in our text. How awesome is that? Imagine you have wrote 500 pages of an amazing book, and then you want to publish it, and there are a lot of duplicates. If you run this tool, this would take like maybe a few seconds or even less really, to go through the whole text and just do that. Match everything, give you the information, and you can do what you want with that information. Great. Next lesson, let's have a look at more examples, more complex examples. Let's solidify our knowledge. Let's do that. See you there.
Let's have a look at a new example. And imagine that you're writing a program to scrap a website and extract all the URLs, or maybe use the URLs to visit them and extract some information from those URLs. In any case, that is a usual program. A lot of those are written, maybe every day even. And let's have a look at how our program can actually understand that a URL is actually a URL, right? And to be a URL, a valid one, it must follow some rules, right? So in our cases, let's assume that a valid URL starts with an HTTP or an HTTPS, and then is followed by a colon and double slash. And then we can either have www dot and then the rest of the URL, or we might not even have that. That is also a valid URL, all right? And then comes the domain name that can contain alphanumerics, or it also can contain dashes, or it could also contain dots. So in this case, www some website.market, and some would be a subdomain of the website domain. So it is valid. It is a valid URL. And then let's have an extension for that URL, for example, a .com extension. And let's assume that the extension can only contain one up to 6 letters. And then there could be a port number, which is represented by a colon and a number of digits. The number of digits could be between 1 and 6. So for example, here there are 4, here is only 1, and here are 5 of them. Oh, sorry, let's do it 1 until 5 because this is actually the maximum port you can define. So let's follow the rules. And there also could be a slash at the end of the port, or if there is no port, it could be a slash at the end of the URL, or it could be no slashes at all. All right. So let me add a space here because we do not want to match this website, this URL. It seems valid, but the extension is more than 5 alphanumerics long. Okay. So let's start. First of all, we should look at the beginning, of course, and we see that we need to match HTTP or HTTPS. And when I'm saying or, you probably see it coming that we need to use alternation, right? So HTTP or HTTPS. Not that HTTPS is not matched, but the HTTP part of that HTTPS is matched because the alternation looks for the first one, and if it matches, it is all cool for it. But we also want to match the whole HTTPS. And that is not a problem as we continue writing our expression that will be matched. So let's continue. After that, we want to match a colon and 2 slashes, right? And note that we cannot use slashes because they do not actually represent slashes, and we need to escape them for them to represent slashes, all right? And then comes the optional www dot part. So this example doesn't have it, this one does. And it is optional, so we write it down and then we use some quantifier on it, on the whole expression. So to use a quantifier on the whole sub-expression, we need to group it in parentheses and then use a quantifier, and the quantifier could be 0, a range from 0 to 1, because it can appear So 1, or it might not appear, which is 0, and it's totally fine. Next, we want to match the domain itself. And as we saw, we can have alphanumerics, we can have letters, numbers, we can have a dot, we can have a dash in there. Everything is acceptable. And we can write a character class for that, as we learned before. So any lowercase letter, any uppercase letter, any digit. And now we want to also match the dash, and in the character class, a dash is could actually be a meta character, so we need to escape that in this case. And then we can match also a dot. And in a character class, a dot is just a dot, while outside it is not. It is a meta character which represents match any character. Now we close our character class. And we know that domain should consist of at least one such character. So let's use a range for that. We can use 1 comma, which means at least one of such characters should exist. Okay. Next, we want to match the extension part, which is a dot, and then comes, well, a sequence of characters up until 6 characters, as we have decided before. And let's see, \w matches any character, any alphanumeric character, and underscore, as we have seen before already. Then we can use a range to define that we want to match a number of characters up until 6, right? And this is what happens. It is matching every one of those. It also matches this one, and that is because it is matching the character group which consists of one or more characters, and it just matches all them in this one because this part is actually optional. We have a 0, and it shouldn't be, but we will look at it later. And finally, we want to match a possible port that exists. So it is optional once again. And to define a port, we have a colon and then a sequence of digits. And given that it is more than one character, we need to group that. So we can define a colon and then a digit, which can be defined by \d, lowercase d. And the number of digits that can appear is between 1 and 5, as we have agreed before, right? And the port itself is actually optional, so it might appear or it might not appear. In this case, we only match the ones that have port. So using, once again, a range from 0 to 1, we match everything else, all right? And do not forget about backslash. I mean, not backslash, a usual slash. We need to match it if it exists. And to do that, we need to escape it, as we have seen before. And you can see that it matches the last 2 examples as they have slashes, but the others are not matched because the slash is actually optional too. So using a range is working fine. Now, this example I've talked before is not supposed to be matching, and well, it is simple to resolve it as we want to match a URL that ends just after this expression. So there is nothing else there. So by adding an end of the expression, this should be resolving, but it is not actually resolving. And let's have a look why. So the real issue here is that this is matching everything here, right? So the character class is matching everything after www dot, because everything else is actually optional, and it definitely shouldn't be, because the error here is that when we match the domain, so this character class, the extension is missing a dot here. Damn, unfortunate. So let's add a dot. So now we match a dot. right? So we're missing that. And as you can see, if you miss some little piece of the regular expression, it can completely break your result. All right. So in the next lesson, let's have a look at how we can actually improve this expression. See you there.
Let's simplify our previous regular expression to match the valid URLs, the URLs that are valid for us, that we decided that are valid, and let's see at what we had before. Note that I also added an example here, which is an invalid URL that is actually matching, so our regular expression is not correct, and it is invalid because there is a comma here, which is unacceptable. So we will have a look at what is going on in that expression we wrote. But first, let's start by simplifying it and making our eyes, well, less bleedy and more happy. So let's see, we have HTTP or HTTPS, that is what we are matching, that is what we expect. We want a URL to start with HTTP or HTTPS, that's totally fine. But note that the only difference between those two words is the S and the in the end. So it is actually just HTTP and then maybe an S appears or maybe it doesn't. So we can simplify that. Instead of using an alternation, I will remove this. I will write HTTP and then S, and it matches all HTTPS, but then S is actually optional. So what we can use? We can use a quantifier here, meaning from that a character can appear from 0 to 1 time. And we could actually use a range here, 0 to 1, but well, why would we use that if we have a shorthand for that range, which is a question mark? A question mark makes a character optional, and that is what is happening in this case, making the S optional. So it matches HTTP or HTTPS. Cool. So the next one is matching a column, and that is fine. We cannot improve that really. And then 2 slashes, and we wrote 2 escaped slashes because slash by themselves isn't just a slash, and we need to escape that. And we actually can simplify it and do not write it twice. We can use a range, but with just one number. That means match slash just twice and exactly twice. And then we are matching www dot once or 0 times. So it is also optional. We can already improve this regular expression by writing a question mark instead of a range from 0 to 1. But now let's see. We actually got to the case that this last example I have added actually matches, and it shouldn't. But why is it matching if you're using a www dot, not a www comma? And that is quite simple actually. You must not forget that dot is actually a meta character, and it matches absolutely any character, right? So if we want to match just a dot, we need to escape that. And look at that. We no longer match the last example I've added here. Cool. And let's look at the difference here between this question mark and the first one. The first one is just applied for the S, alright? But the second one is applied for a group, a sub-expression, okay? So we can assume that S is a sub-expression. That is totally fine. A sub-expression that is just a 1-character expression. And if we want a more than 1-character sub-expression, we need to group it by using parentheses. Alright? And then we can apply a quantifier to it. Cool. Now we want to match the domain. And domain can be a lowercase letter, an uppercase letter, a digit, a dash, and it also can contain a dot there. And we know from before that we can match A to Z, uppercase and lowercase, and 0 to 9 using \W, right? It matches any alphanumeric and underscore, and then we can leave the rest be there because it cannot be matched by the W, unfortunately, but that's totally fine. And this is a great simplification. Look at the size of our regex. It is getting smaller and smaller. Very cool. And we cannot actually simplify anything else here in this character class because it matches or alphanumerics or a dash or a dot. Well, nothing really to simplify, but we have a quantifier applied to it, and that can be simplified. A range that starts with 1 and can go to whatever you want, so any number of characters as you want, can actually be shorthanded to a plus sign. As you can see, nothing changed because plus means once or any other number of times higher than 1. And that is a good simplification here. And then let's look at the dot. We're using a dot and then an extension. So we must have an extension, right? And a dot represents the start of the extension and then the extension itself. And let's see, why do we actually have parentheses here around the dot? Well, we do not really need them, right? Why would we do that? It just adds complexity to our regular expression. It adds absolutely no value there. So we match an exactly dot. We need to escape the dot. Do not forget it. And then we match an extension, and as we agreed, an extension must have at maximum 6 alphanumerics. And it actually must have also at least 1, right? Otherwise there is no extension. And having something like this should be matchable because it is not a valid URL. So what is this? A dot, then a colon, and then a port number? What the hell? So we actually need to trim this expression and add 1 here. So the number of characters of the extension should be between 1 and 6. And now comes the port part, which is a colon and then a port number, which can consist from 1 to 5 digits, as we decided before. And as you can see, it is also optional, so it can appear 0 or 1 time. And let's substitute that by a question mark. And then we have a slash once again at the end. It could appear after the port or even if there is no port. So a slash, which is also optional. So let's add a question mark there. Nice. We simplified it quite a bit, you know. It might still seem complex, but if you read it through, it is quite easy to understand what is going on. So let's read it. Do not hesitate to read your regular expression and understand whether it is seamless or not, because other people might read it, and if it is not obvious for them, then your regular expression should be trimmed a little bit. So let's see. So we want to match a string that has HTTP or HTTPS, because SN is optional, then a colon, then 2 slashes, and then a www dot can appear, or it might not appear, and then any number of characters, alphanumeric characters, or dashes or dots, and then a dot, and then we want to match 1 to 6 characters, which is actually our extension. And then we have 2 optional items. We can have a port, a colon, and 1 to 5 digits. And we can also have a slash there, or we could not have a port because it is optional and have a slash there, or we could have a port and not have a slash there. So that's really it. Those are all the examples here. And as you can see, we didn't match what we actually didn't want to match. So this is great. We improved a lot. If you keep doing this with your regular expression, it is just fantastic. Just do not forget that you shouldn't do it in the beginning of writing it. You should do it after you wrote something and you know it works. All right? So in the next lesson, let's have a look at another example our examples will continue to getting more complex from lesson to lesson. So see you there.
Let's continue to look at our examples, and let's also continue with our web scraper example. And in this case, we want to scrape a web page and find all the valid HTML tags, and then our tool might return them to us, and we may or may not use them as we wish. So, what is a valid HTML tag? And that is something that is something like those three examples first, the first three ones, and not the last one. So starting from the first one, it is an h1 tag. We open the tag with a lower than sign, and then the tag might have some attributes like style attribute, and it has some configurations here. And then we close the opener and write some text, or maybe add another tag in there, just whatever you want, and then close the tag. And to close the tag, we use slash and the name of the tag, and we just close it. So several examples of the valid tags are a tag with some attributes, and another tag with attributes, a simple tag with no attributes, and actually an invalid tag that shouldn't match. So we start a div tag, and then we actually close an h1 tag. And how can we close something we didn't open, right? So this one shouldn't match. And how can we match all those first three and not the last one? So you might have noticed that the tag starts in the beginning of the tag, there is actually the name of the tag, and in the end there is also a name of the tag, and the start and end of the tag are enclosed in the less than and greater than signs, right? So we can use that. So we know that when we want to start a tag, we want something like this. We need a name there. So we got the greater than and less than signs, and we need the name of the tag in there. And to match the name of the tag, we should be matching any alphanumeric. And for that, we already know it is \w to match a character that is alphanumeric or underscore. And the amount of such occurrences can be at least one, but can be much higher, because you can define your own tags and you can define something really large. So let's use a plus sign. That means we want to match at least one character. That is the name of our tag. So we already matched the name of our tag. And then we can have any amount of attributes there. And to match anything, as we already know, we can use a dot. It matches any character. It is a meta character. And well, you can have attributes, or you might not have them. So we need to use a quantifier that tells us about that. And what quantifier means 0 or more? Yeah, that's exactly this one, the star or asterisk, right? Note that it already matches some of the occurrences we have here, the first one and the second one. They match them because the dot is actually matching everything, and the asterisk here is matching any number of such occurrences. So match anything any number of times. And then we have an enclosing sign that we also have in the end of our tags here. But why doesn't it match this one? Oh, that's because we have added a space here. It is not required, because a space can also be matched by the dot. So in this case, if we remove the space and just leave the dot, it means that, well, if there is a space, match it. If there is none, do not match it. That's totally fine. So now we've got our entrance to our tag. Now we have the text. So the text can be really anything. Like, we do not care about that. We just want to match valid tags. So once again, let's use something that matches absolutely anything. And then we want to enclose our tag. So close it. And we know that it is the closing part is also in its closing greater than sign and lower than sign. But there is an addition of a slash here. So slash and then the name of the tag. And slash actually represents itself, but not in this case, because we need to escape a slash. And now we want to match the name of the tag that we got here. And well, we can't really do that because we didn't use the capturing group, right? We forgot about it. So we need to enclose this matching in parentheses to make it a capturing group. So now we somewhat save it in memory, what we have captured here, and now we can back reference it. So we can back reference the name of the tag. So if we do so, back referencing the first capturing group and the only one, we get what we wanted. As you can see, the last one doesn't match because we actually back reference the div, and it is not a div, it is h1. So just to recapitulate, we want to match this sign, then the name of the tag with this capturing group, then match anything if there is anything like attributes, and then close, and then match the text or anything that could be inside the tag, and then the closing part, which consists of a slash, and then back referencing the name of the tag. Quite simple, right? And this is very useful because if you write a tool that goes through some source code of some really large page, it can extract all the valid tags, or even you can even define what tags you want to extract, like h1, only h1, or div tags. And you can use that in order to make your tool or program even better and create even your software as a service, maybe. Who knows? All right. So that's it. We will have one more example, the last one for this section, and let's see what it is. See ya.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
One more example on its way. So this one is a task to match lines of text that contain either 3 comma-separated numbers or 6 or more comma-separated numbers. And the examples we have here, that for the first line are 5 comma-separated numbers, so it shouldn't be matching. For the second line, there are 2 comma-separated numbers, then no number, and then 2 more comma-separated numbers. This line also shouldn't match. The next one are 3 comma-separated numbers, and that is what we want here, right? So that should be matching. The next one are 6 numbers, that is what we want too, 6 or more comma-separated numbers. And the next one are 7 numbers, so exactly 6 or more comma-separated numbers. So the last 3 should be matching, while the first 2 examples shouldn't. And let's see how we can do it. So we already know that we are working with digits and we want to match a digit. And well, we could do that, but before we actually get into writing regular expression, we need to understand our approach. And by reading the task here, we see that it says 3 comma-separated numbers or 6 or more comma-separated numbers. So this task already gives us a hint on what we should be using like a base for our regular expression. And that should be alternation, something or something, right? So now that we have this base, we can actually think of how we can do that. And for the we want to work with digits and we want to match digits. So we are probably going to use a shortcut to matching digits. And that should be \d. So as you can see, it matches absolutely any digit you want and whatever there exists from 0 to 9. And a number can contain at least one digit, because if there is no digit, it is not a number, right? So we need to match at least one digit, and that could be achieved by a quantifier that is a plus sign. One or more matches should be occurring there. So as you can see, we are matching all the numbers, and that's a good start, but the numbers should be comma separated, right? So as you can see, well, we need to match a comma too. So adding a comma matches what we want, right? Now, let's look at the criteria here. 3 comma separated numbers. Let's start by this one. So we need 3 of those occurrences, correct? And so we probably need to apply some quantifier that means 3 occurrences. And we already know that applying quantifiers for a expression that is larger than just one character, it requires the expression to be enclosed in parentheses. So in order to apply a quantifier to a sub-expression, we need to close it in parentheses, so we kind of catch it. So a capturing group, I guess. And then apply a quantifier. And we can just write the number of occurrences we want. And it is basically a range from 3 to 3, which is 3. As you can see, the first example partially matches, and it shouldn't be, so something is not correct. The second one isn't matching, that's fine. But the most important part is that the third one isn't matching, and it should be, because it is 3 comma separated numbers, just like we have here, right? There. And it is something you should have in mind in regular expression, because not when you are matching for some similar stuff like we are doing here, numbers and then comma, it is not always the case then that the similar things will appear until the end. Because in this case, it doesn't make sense to have a comma after this number, because there is nothing after this number, right? So we should take that into account when we are writing our expression. So in reality, we just want to match a number, a comma, so a number, a comma, a number, a comma, and a number without a comma there, right? So a number and a comma should occur only twice. And then we should be matching another number, which is a bunch of digits, at least one. Now we got what we wanted. We are matching our third example as expected. Cool. Now let's move on to the 6 or more comma separated items. So as we saw before, we need to use or, so alternation, that is this guy here. And well, 6 or more will be kind of similar to this. So we can start by matching digits and commas. And we need to match this time at least 5 such occurrences. And to match at least 5, we can leave an open-ended range starting from 5 and not ending at all. And why would we need to match 5? Because 5 of them are comma separated and the last one doesn't have a comma after it. So we do not want to match a comma. And at least 5 because we want to match at least 6 numbers. So, and we need to match the last one here, of course, right? And this is something good here, but it is not finished yet, definitely. And something is surely missing, because this last one is not matching correctly. And why is that? Oh, that is because we are not using our firstly learned meta characters. And well, how and why we should apply them? Also, because this one is matching, the first example. And we know that we need to match each line. So it should start by a number and should end with a number. So we can add here starting position. And before the alternation, we want to cut the line here. So now we match those three, right? The third example. And we need to do the same for the next one. even though it matches, it should be required to edit, because there could be examples that I'm not sharing here and that will work, and we do not want them to work actually. All right. So we are matching what we wanted. Must takeaways are do not think that if something occurs like 3 times in a row, it will occur forever, like with this number and comma. You always have examples before actually starting to write a regular expression. You need to extract all the rules for your expression before you start writing it. Otherwise, it is just a waste of time. You won't get anywhere. All right. So yeah, in this case, we used almost everything that we learned. Just what we lacked were character classes, and we can encapsulate something in a character class. It doesn't matter really here. Like if you encapsulate the digit here, it still matches, but we do not need that verbosity here. All right, that's it. Congratulations. You finished the second section. Nice. Let's have a small video on what we have learned so far and take some takeaways. So see you there. Hello and welcome back. Let's have a look at the summary and caveats of what we have learned so far in our section 2. Mostly we learned about quantifiers and capturing groups, but there are also some use cases that we had a chance to look at. And some of them are that we learned a new shorthand for word boundaries, that is \B. Quite useful, but it is not very used. You will most likely use \W, \D, and so on. And maybe sometimes \B will come in handy. So do not forget about it. The second thing is we have actually talked about the dot meta character before, but in this section using the quantifiers it became even more important. And you will find yourself using the dot meta character to match any character with quantifiers quite often. So use it and abuse it. The next one, we learned how to escape a meta character, and it is just to use a \, and then a meta character, and it will start meaning exactly what that character represents. So for example, if we use \, and then a dot, we want to say that we want to match exactly that dot character, right? So the next one, the next slide here, is about the ranges. It is a type of quantifiers that quantifies a number of occurrences of some character or a capturing group, and it is defined by curly brackets here, and then inside them you can have the minimum value, it is a digit, and the maximum value, and none of them can be less than 0 because a range is positive. So you can define that, which means match a character at least min times and at most max times. Then you can also use curly brackets, but with only one digit in there, which is meaning that you want to match exactly some number of times. In this case, a character would be matched exactly number of times, assuming this is a digit. And there is also another approach, is to use just the minimum value and then a comma. And it means match at least minimum number of times. All right. And we also learned about other quantifiers, and that are a question mark, a plus sign, and a star or asterisk. And they just really represent some sort of a range. And they're quite useful as they take less space than writing a range that you would like to write. So we learned about optional character, which is a question mark, and it means exactly the same as a range from 0 to 1. So it means match or do not match it. I am fine with both. At least one character which is a plus sign, which is meaning exactly what the range from 1 to, let's say, infinity or an undefined number here. So match at least one character, and it is a shorthand for that. 0 or more characters is a star, and it means the same as a range from 0 to undetermined number. And well, those three, you will find yourself using those three quite often. You will also find yourself using ranges sometimes, but not as often as you will find yourself using the optional character, the plus sign, and the star. And quantifiers along with ranges are applied to a single character or a capturing group, and a capturing group will be summarized in the next slide. But so do not forget that if you want to apply a quantifier to something, an expression that is longer than one character, you will want to enclose it in parentheses to make it a capturing group and then apply a quantifier to it. So what is a capturing group? A capturing group, it is basically parentheses which have some stuff in it, a sub-expression. So it allows you to capture something, so match something and save that information in memory, let's say, and then later reuse it. And well, as mentioned before, you can apply quantifiers to it. And there is an example of a capturing group here. It is capturing one digit, and later on you can reuse it. And to reuse it, we will have a look later because it is back referencing actually. So the next caveat is that parentheses that we learned and used with alternation are actually a capturing group too. So if you recall, we use something like open parentheses, A or B and close parentheses, and it would be matching A or B. And the parentheses actually do not just help us to identify the scope of the alternation, but also capture the result of the alternation. So you can use that result later on. And to use the result later on, you should be using something called back referencing. So, well, what it does, it is in the name. It back references something that you have referenced before. And to use it, you use a backslash and then a number of capturing group. So really capturing groups and back referencing comes together, but you do not really need to back reference if you use capturing group. You can use capturing group for some reason like, well, alternation, but you don't really want to reuse that match. You can use that, but you don't need to use the back reference, right? And to define a back reference to some capturing group, you use backslash and then the number of the capturing group. And do not forget that capturing groups are numbered by the open parentheses. So if I open parentheses, that is the first one. If I next open another parenthesis, this is the second one, and so on and so forth. So you also cannot back reference a non-existing capturing group. How unexpected is that, right? So if you have an expression with just one capturing group, like for example here, it's capturing ABC, you cannot back reference a second capturing group with \2, for example, because it doesn't exist. Also, be careful with unexpected escape of the capturing group. So this is an example. We want to capture ABC and then any number of characters and be that any character. And then we want to back reference ABC. But we mistype it, and as we learned before, a backslash with a meta character, which is \1, which is a sub-expression that is something meta. You're actually escaping it, right? So what it will mean is match ABC, then anything, and then backslash, because it is escaping backslash, and then just one. So this is not what you want, right? Be careful with that. All right, so this is all for the summary and caveats for the second section. And in the next one, we will be learning even more advanced stuff. And stay tuned for that. Up until now, up until this section 2, you basically got all the information to start writing your usual regular expressions. You will most likely use only this information to write your regex, but what comes next is actually what will improve your regular expression and make it even more, let's say, well, it will have a lot more features. Let's put it like that. All right, so see you in the next lesson, I guess. All right, welcome. Welcome to the third section of this course. And this one will be a little bit more advanced, as you would expect. And we will be talking about something called lookaround, which actually consists of two parts, a look ahead and look behind. This is something not really very used because people do not actually know about it. What we learned up until now, so until the section 2 about character classes, shorthands, quantifiers, is what you will be using the most when you write regular expressions. But it doesn't mean that you shouldn't be learning something extra. What will make your regular expression even more powerful, right? You can match absolutely anything. Maybe you can match like something and go to Mars. I don't know. Who knows? So, what is actually look around? And, well, look ahead. Let's start by look ahead. Look ahead is what does it really mean? So, when you want to match something, if something in the future occurs, that is look ahead. That is a positive look ahead. So, what I mean by that, an example. I want to match the character A if after the character comes B and C. Cool, it will match ABC, but it won't match the name N, for example. So this helps you to make your expression even more powerful, and it brings in a lot of new features. So this is the positive look ahead. The negative look ahead would be something like, I want to match the character A if there is no B and C after it. So in this case, ABC wouldn't be matched because after A comes the letter B and then C. The other part is we have look ahead and the other part is look behind. And that's, well, as you would expect, it is something similar to look ahead. And it basically means I want to match the character A if before it we had characters Z and Y, for example. So that is a positive look behind. While the negative look behind would be I want to match the letter A if there is no Z and Y before it. And I'm giving some really simple examples here, but your before or after part can be something really large and that will match a lot of text. Although it is not really performant if you do so, but that is something to tackle in the future. First, do not forget, write your regular expression, make it work, and then optimize it. So we will be looking at that. Look ahead, look behind, and if you combine them, that is called look around. As I mentioned, it is not widely used because people don't really care too much about it because they usually do not need to use it. But if you will know it, congratulations, you will be good at it. And the whole regular expression stuff, to be honest. It is like the last part of the stuff you actually need to know to be a pro in regular expressions. Well, in writing them, you need also to be a pro in actually understanding what is happening behind them. So that is something to tackle. So cool. you will learn it, and let's have a look at it in the next lesson. See ya. Welcome, welcome. And in this lesson, we will be looking at the lookahead assertions. And as you might have noticed, the lookahead assertions has assertion in its name. And it applies to all looking behinds, looking ahead, be that positive or negative. The idea is that assertion doesn't really capture the text. So it actually matches, but then it releases the match and moves your position, let's say, to before it actually matched. So for example, if an assertion matches movie in this string in the first one, and you have some regular expression after it, your regular expression after it will start from the before the movie starts. So we actually match it, yeah. Assertion assert that it can match it, and then their usual regular expression starts to match the text. And let's see what that means in a practical example. And for this example, I added some superhero names: Superman, Ant-Man, Catwoman, and Banana Man. This one is a new one. He drops bananas, and people sleep on it, and they lose, and he wins. And then a movie title. Let's assume that they are just movie 1, movie 2, movie 3, and 4. So we will want to be matching the strings that contain a superhero name. Now I also added some strings that we shouldn't be matching, and it is banana phone, cat lead, and super duper awesome. So as you can see, some of the words also appear in some of the superhero names. So let's see how we can do that using assertions. As usual, when you write a regular expression, you first need to understand what is similar between the strings you want to be matching. And in this case, all of them have man in the end of the superhero name. So we can do that. But you also only want to match this string unless there is a you want to only match a string, Superman movie 1, if there is a superhero name in there. So we can actually look ahead of our match, and if there is a match, just match everything. And how we can do that? So for a look ahead, a positive one, what we're going to use is to first delimit the look ahead by parentheses, and then use question mark and equal sign for the positive look ahead. All right, so it means, well, look ahead, and if something matches what you're looking for, then continue with your regular expression, and otherwise just say you cannot match anything. And as we have seen, we want to match man, the word man, the letters MAN, and we can do so. So as you can see, it doesn't really match anything. It matches null. So it doesn't really match anything because we are just looking for the existence of a string man in each of the lines. And in some of them it exists, but then we have no real regular expression to apply to the strings. So as I said before, it matches the man, the word man, but it doesn't mean that regular expression matches it. So be careful with that. Do not assume you can match it, but there is a way to do so, and I will show it later. So imagine that we now know that there is a man string in your initial string, and then we just want to match everything. So we start from the beginning of the string, okay? Because this one is dropped. And what we could do, just match everything by dot and asterisk. And as you can see, it actually starts from the man position, and that that is what I have mentioned. If you want to match assert over movie, it matches movie, but then it moves the position to before it actually matched movie. Okay? So it is not what we want, because we want to match everything, right? And how we can do that? So we know that a superhero name has a suffix of man, but we cannot really reuse it, right? So we can't reuse this match unless we use a capturing group. So it is possible to use a capturing group inside an assertion. And if you, if you use a capturing group here, we can now back reference man, and it actually matches because it is a capturing group. Now note that those first parentheses, this one, the opening one, and this one, the closing one, is not actually a capturing group, and it just delimits the assertion. So do not mix those. And now we are matching man, right? So what we could do is now use something like anything. So start to match anything, and then look if there is man in your string, and then match anything else. So this way we can match anything, right? Anything we want. But there is another way. Sorry, we added a capturing group, so we can actually use this. A back reference. Now, not that this appears to be matching, but it is not actually matching. Okay. So when we use this, a dot and a asterisk, and then a dot and asterisk, what happens is that, hey, the regular expression matches everything, then looks for an existence of man, and then matches anything. So it doesn't really match man itself, it matches anything, and man is part of anything. Okay? So if we want to make sure that we actually match that, we can use \1 for referencing the man word, and after that, just match anything. All right? So this way, we have all we wanted. So it is possible to actually reuse what you're asserting over here, and that is quite useful. So in the next lesson, let's have a look at a negative lookahead assertion and how we can use that. So see you. Now the negative lookahead. So the objective of the negative lookahead is to actually only match what you want if there is not something you don't want in the future of the string. And let's apply it to this example. As usual, an example is much better than some theoretical explanation. And in this case, what we have is let's assume it is a database, for example. It is an output of a query to database, and we get a serial number, a vehicle type, be that car, boat, or anything else, and status of that vehicle, whether it is sold, not sold, or whether it is in repair. And of course, we could have been using queries to query the DB to get the information we want, but let's assume we cannot do that, and we have this information. And what we want to do is to match the cars that are not sold. Okay, so goal, match cars that are not sold. All right, so in this case, it would be the second one, a car which is not sold, and the fourth one, which is in repair. The fifth one is a boat, so it doesn't work, even though it is not sold, right? So we shouldn't be matching this. The objective, the goal is here to match the second one and the fourth one. And how we can do that with a negative lookahead? It is also possible to apply positive lookahead here, but let's apply a negative one. So what we want to match, first of all, what is here? Match cars that are not sold. So we probably want a vehicle that is a car, start by matching car, cool. And now we see that there could be any amount of spaces in between car and its status, whether it is sold or in repair or not sold. And then there shouldn't be a word sold right after the spaces. So there could be a lot of spaces and be not sold or be in repair or anything else really. So we basically want to apply a negative lookahead for that. And it is a perfect example where you will really use this negative lookahead, and it is very useful here. So how do we do that? As before, in a positive lookahead, we need to delimit the lookahead and note that this is not a capturing group. Lookaheads are not being captured. And in the positive one, we used a question mark and equal sign. But in this one, we are going to use a question mark and an exclamation sign, meaning not in some programming languages, in most of them, I would say. And then you can add your regular expression. Okay. So in this case, what is coming after the car? What don't we want to match after the car? So it would be a number of spaces, any number, and well, at least one space, right? And then the word sold. We don't want to have that. So we already know how to do that. Any number of spaces, \s to match any type of space, and then a plus sign, so one or more. And then what do we want? Or actually what we don't want is sold. Look at that. Oh, well, ignore this one. It is just the problem we are tackling. So look at that. The car in the second line matched and the car in the fourth line matched. Nice. So what does it mean? Let's go through our regular expression once again. We are matching a car. This is just a car match. And then we are looking into the future of our string, right? Just after the car, for example, here. And we do not want for it to be any number of spaces, at least one, but anything above one, and then the word sold. We don't want that to be. If it is the case, so asserting over it, if it is the case, then do not match that string. Okay. And that is what is happening here. Cool. So now you extracted the information from the database. Nice. So in the next lesson, we will be looking at a positive look behind. So stay tuned. Positive look behind this time. It is quite similar in syntax for positive look ahead, but well, there are some differences. And let's have a look at a simple example and then move on a more interesting one. So this one is just a text saying hello Regexers, and the goal is to match the E that comes just after the G. So as you can see, it is this one, an E that comes after the G. And when you write your expressions with assertion, you will need to start by what you actually want to match. In this case, we want to match an E. All right, so if we just leave it like that, we will just be matching that. Everything, every E, right? But now we also need to add something that tells us that before the E came the G. And if you just add G, it is matching G and E, and you don't want to. Your goal is to match just the E, and you're matching G and E. That's incorrect. So you need to use a positive look behind, and for that, just like with look ahead, you need to delimit it first with parentheses. It is not a caption group, all right? And the syntax for positive look behind is something similar to look ahead. And for look ahead, we have a question mark and equal sign. And in this case, we just need to add between the question mark and equal sign a less than sign. So it is visually telling us, hey, look behind with this sign, right? And we want to match a G behind E. So we just add that. Not that it matches the E that we wanted, okay? And let's see how the regular expression is evaluated and applied to our text here. So first, it will be looking for the E because it wants to match E and only then look what is behind the E, okay? So it goes for H. H is not an E, so it doesn't match. Then it goes for the first E after the H, and now it will use our assertion on positive look behind and see if the previous character is a G, and it is not, it is an H. So it just keeps on going until it matches the E again. And now looks back, it is an R, it is not a G, so it doesn't match. And it goes on and matches this E and looks back, it is a G. So the expression stops here. It is no longer evaluated, it is a match. It is cool, it is what we want. All right. So now let's have a look at an example. a more elaborated one, and I will copy paste an example I have here. And the goal would be to match all the USD values. Okay, so imagine that this is some data from database, for example, and we have currencies, USD, Euro, and some other ones, and then some values for them. So maybe a cost of some service. And imagine that we use USD and we only want to know that cost. All right, so how we can do that? First of all, we want to match the cost. Do not forget, start by what you want to match. And to match a cost, it is only digits. Let's assume it doesn't have any commas and some other digits. It is just a combination of digits, and you know how to do that already. It is a backslash lowercase d and a plus sign. Matches at least one digit. So we got it. Okay, cool. And what needs to come before it? So before it, there is a currency and then a space. And yeah, let's use positive look behind. Let's delimit our positive look behind and write the syntax for the positive look behind. And now we want to just match the USD ones. So it is as simple as writing USD, and it is not matching because there is a space, and just adding space. So as you can see, all the USDs are matching, USD 100, USD 70, and USD 500, and no other are matching. Okay, so let's go through the expression once again, just to make sure we solidify our knowledge. So first of all, the expression will be applied and it will be looking for at least one digit, and it will find the first digit in any of this line at this column here. And then it will be looking behind and it finds the space, right? It will find the space in any string before the first digit. That's fine. And then it is looking for the USD. And only in these three cases, it finds USD. So it matches only those three. Okay, awesome. This is another useful application of lookaround, and in particular, look behind. So let's see the negative look behind in the next lecture. See you there. Let's have a look at a negative look behind this time. And the example is what we had before for the positive look behind. But now imagine that what we are selling here is no longer sold in Japan, for example, and we want to remove this Japanese yen price. So we want to match everything else and then just remove what we don't match. So the idea is to match the digits here, right? And do not match this one. And how can we do that? As before, and as always, start by what you want to match. And you want to match digits, so that is backslash lowercase d and a plus sign to make it one or more digits. And then we need to use negative look behind. And the negative look behind is also delimited by parentheses, not a caption group. And the syntax is quite similar to negative look ahead. So as we have seen, the negative look ahead is something like this, a question mark and an exclamation mark. And a negative look behind, as you might have noticed in our previous example, just adds a new character in between them. So that would be a less than, or a less than sign. Yeah. So it visually tells you, hey, look behind. So what we want here is to not match Japanese yen. Okay. And as you can see, it is matching. Well, that's because we need to add a space. It is still matching. Oh. So let's see what is actually happening here. First, our Regex is applied to this text. And how is it applied? It first looks for the digit, one digit. So it goes for J, P, Y, space, and those are not digits, so it skips it, and goes for the first two, right? This one. and then it looks back. And we don't want it to have a JPY space before it, but it has, so it doesn't match. Okay, that's fine, but the regular expression doesn't stop there, and it is applied for the second digit. So the second 2 doesn't actually have a JPY space before it because it has a 2 before it, right? So this 2. So it is actually matching. From here on, it is just matching. And how can we do that? So you might think that, well, we can say that we want a space or a digit. And why a digit here? Or not or, just space and digit, because, well, that is what is happening here, right? It is a JPY, a space, and then a 2. That is a digit. So we don't want to match that. That's fine. So what we could do is add \d here. And what is going on now? Now it is matching everything again. And that is why, that is because when the first 2 is matched, there is no longer a digit before it, so it is matching. But we added this condition that we don't want a digit before it, and there is actually no digit before it, so it is matching. So what we might think we should do is making this digit optional. So for example, JPY space 1 shouldn't actually match because before 1 there is no digit, but then JPY 22,000 should be matching, should not also be matching from the second 2 because there is a digit before it. So we might think that making it optional might work, and that would be a correct assumption, but it doesn't really work. And it doesn't really work in most of the tools that apply regular expressions, but in some of them they work. And the reason behind it is quite simple. It is to prevent people who write regular expressions to create regular expressions so complex that they take a lot of time to process and be applied. And that is actually what is called, I think it is called pathological syndrome or something like that, when people just start applying a lot of knowledge in regular expression, making it just really hard to, maybe not hard in this case to read, but really complex. And they do not know what is happening behind, and that is adding a lot of overhead, actually. So not allowing to use quantifiers in lookbehind is actually something to help us, I guess. But in this case, it doesn't really help. So how can we do that? Going back to our previous solution. So let's see, we don't want to match a JPY and then a space and then a digit. Okay. So what we could do is actually not match JPY and just match digit. What about that? Doesn't work either. So we need to add a space here. Okay. So now what is happening, it is looking for the space and then it looks for JPY before it. Okay. And that is why those lines are not matching. But now our regular expression is actually matching a space and a digit. Quite unfortunate, isn't it? So this is one of the cases where you need to make some trade-offs with your expression. You most likely, in like at least 50% of the times, won't find a perfect regular expression for your use case, but you can always do some manipulation over it in order to achieve your result. And in this case, it would be possible to maybe, well, apply some substitution after using this regular expression to remove the spaces. That is an example. Just substitute the spaces that you have matched by nothing, so it removes it, right? That is one solution. So do not worry if you do not find a perfect regular expression for your use case. It is always doable and you will find a solution for sure. So this is it for lookarounds. And in the next lesson, we will have a look at a more complex example to even more solidify our knowledge, right? Hey, so in the last lesson, we had this example and this solution, which is actually not perfect because it is matching a space too before the digits. And I told you that you could resolve your achieve your results with applying a regular expression and then doing something over what has been matched. And that is absolutely true, and you will find yourself doing so maybe quite often. But do not forget that knowledge in regular expressions will lower the chance of you having to do extra work. So do everything with what you have learned for regular expressions. And this is not an exception. So it is possible to achieve our result with just a regular expression. And how we can do that? So I didn't alter anything from the last session we had, and we are matching the space and the digits, and we are not matching the Japanese yen entries, but we only want to match digits. And what we had before was something like this. This was the issue, and that's fine. So another cool thing about lookarounds is that you can have several lookarounds. So imagine that this is an OR operation over multiple lookarounds, be that look behind, be that look ahead, just really anything. You can have as many as you want, but do not forget that it's quite it will be adding some overhead over your regular expression and its execution. So be careful with that, don't overuse it. And what am I meaning by having several, well, in this case, negative look behinds? That is exactly what we need to achieve, right? So what we want is that we don't want before the first digit have a space and Japanese yen. But also we don't want to have before any digit a digit and then the Japanese yen, the space and Japanese yen, right? Or just a digit actually. So what we could do is add another negative back reference. Sorry, look behind. Sorry, and that is how we do it. A question mark, less than sign, an exclamation mark marks the negative look behind, and then we don't want to match any digits. How cool is that? So what really happens here? Let's have a look. So what changed for other text? So let's consider this one, the first one, the USD 100. Well, we still continue to look at the digits, and we go for the 1 here and then check. There is no digit before it, and there is also no space in Japanese yen before it. So that's cool. We're matching it. Okay. So if we change something to something like this, it would no longer match because one of those look behinds would actually be true, and we don't want that. It is a negative look behind. And so really this is, I think I said it was an OR operator between look behinds, but it is actually an AND operator. Sorry about that if I said that. So we do not want to match nor this, nor a digit before our digit, nor a space USD before our digit, right? So let's get back to our Japanese yen, JPY. And let's see what is happening here for the Japanese yen. We are looking for a digit and we find the 2 here, and we look behind and there is a space and JPY. So this look behind tells, hey, that is not what we want. No, please abort. So it is aborted, and we apply regular expression for the second 2. Okay, And in this case, there is no space in Japanese yen before it, but there is a digit before it. So this negative loop behind says, hey, hold on, we are not matching this text, move ahead. And that is what continues to happen actually for the 0, for the next 0, and the next 0. So before each of those zeros comes a digit, and we don't want that. And this is the solution for our problem. Even if you wouldn't get it, that is absolutely fine. You can apply some substitution. Even it is quite common to apply substitution after you apply your regular expression. Okay. So in the previous case that we matched a space and some digits, it is also very easy to remove the space before the digit. So it is really not much work. But if you are matching something with your regular expression and then you have to do a lot of extra work over it, well, you might want to apply some advanced learnings of regular expressions. Okay, cool. So as I said in the previous lesson, and I actually lied to you, I said we were going to look at a more advanced example, and in this lesson I just tricked you and told you that regular expressions are actually very powerful, and you most likely will find a solution with just regular expressions. But I won't lie again, and in the next lesson we will have a look at a more advanced example. You will like it. See you. Hello. Did you miss me? Because I surely did miss you. And let's have a look at an example for our lookarounds. It is a little bit more real example, as anybody would prefer, really. So what it is, the goal is to match a password, and a password has some rules. So a string has some rules to be considered a password, and that is to be between 6 and 12 characters in length. It should have at least one uppercase, one lowercase, and one digit. And it should also contain a special character. And here are some examples of a special character. It is a dollar, a percentage sign, caret, or a space. For example, it could be anything else like this. Now, we have some stuff we do not want to match. So those are not passwords. All capitalized letters A, all lowercase letters, all digits. Then we actually have a lowercase, uppercase, a digit, and a special character. But this text is not between 6 and 12 characters, so it is not considered a valid password. In this case, we have a text over 12 characters, so that cannot be considered a valid password either. And this one doesn't have a special character, so not valid. And we have 3 examples that we want to match. It is an easy password with a 3, a lowercase letter, an uppercase letter, a special character, and all of them have these characteristics, and they all are of length between 6 and 12. So let's see how we can actually match it. And as you might know, of course, when you input your password, there is usually a place on the site, for example, or in your app, where you need to input that. And we need to make sure that it is just one line. It is not some text or, several lines of text or something like that. So we know how to do that, and it is to use our meta characters that define the start and the end of the line. So the caret and the dollar sign. And now there are various possibilities of matching such passwords, and in this case we are going to use positive lookahead. So the idea is to validate before we actually match the password whether it has a one uppercase letter, a one lowercase letter, one digit, and at least one special character. Yeah. And how to do that? So we already know that to define a positive lookahead, we need to delimit it with parentheses and then use the positive lookahead syntax, which is a question mark and equal sign. And now what do we want to assert over? So we want, let's start by this one, must have at least one uppercase letter. So we need to assert that there exists one, or at least one, doesn't matter, one uppercase letter. And how does this work? So we can really assert that there is anything, and then after anything comes an uppercase letter, and then the assertion is true. And how can we write that? So anything is really a dot, but it just matches one character. So we need to use something like dot asterisk, which matches anything for any amount of times, be that 0 or 100 or whatever. And then we want to match an uppercase letter, and we can use a character class for that, from capital A to capital Z. And this lookahead asserts that in our text there is actually a capital and uppercase letter, right? And for the other options, the lowercase and the digits, we can actually copy these, copy-paste driven development, right? And just change the character class that we want to assert over. And for the lowercase, it will be a range from the lowercase a to lowercase z. And for the digits, it could be a range from 0 to 9, but we know that there is a shorthand for digits, that is a \d. So now we can see that we're actually asserting that there is an uppercase, a lowercase, and a digit in our possibly valid password. If those assertions are fine, we also want to assert over a special character. And we can paste again our expression, and we need to change this character class by something else. And a special character is really anything that is not alphanumeric or underscore in passwords. And that can be represented by what we have learned already. It is a negated character class. So instead of thinking that we want to match any special character, we can think that we want to match anything that is not alphanumeric, right? And that is what we can do here. Instead of writing all the special characters, just write a negated class, negate \w, that represents an alphanumeric. Cool. And well, we asserted over those 4 conditions, the last one, but we did nothing for the first one. And well, let's look at our expression. We assert, but remember that when we assert, we don't actually match anything. We just assert, okay, this assertion is true, there exists a uppercase, a lowercase, a digit, a special character, cool. And now we actually want to match the password and assert over its length. And when we are talking about length of something, we must use quantifiers. So to assert now, we do not care what the password has, because we validated that it has the stuff we want. So we can match anything. For that, we can use a dot. It matches any character. And now we need to define a range of how many times it matches any character, and it will be between 6 and 12. That is our regular expression that matches all the stuff we want to match, but it also matches one thing that it is not supposed to be matching. And that is a invalid password that doesn't contain a special character. So why does it match? Let's see it. Let's look at our expression. So it has an uppercase, okay, it passes. It has a lowercase letter, okay, it passes the second assertion. It has a digit, so passes the third one, but it doesn't have a special character. What is going on? So be careful with when you write negated classes, because in this case, the negation of alphanumeric actually matches a new line. Didn't expect that, right? So this is what is happening in this case, okay? And to stop that from happening, just add a new line to your negated character class. And that's it. This is one of the ways you can match such a password. And surely there are other ways, but this one is pretty cool, I would say. So hope you like it. See you in the next lesson, and we will be having a look at another cool example.
It's break time. Do you like this video? Don't forget to subscribe to get new videos. Share this video to open new premium videos and ebooks. We'll be a star freelancer.
Are you ready for a new difficult example? Here it comes. So the goal here is to extract every word that is not a variable from an interpolated string. So what is an interpolated string? It is a reference to software engineering and programming and writing code. And an interpolated string is something like a string, and then it has some characters, like in our case, it will be hashtag, open curly parentheses and close curly parentheses. And this combination of characters is actually intended as something else rather than normal string, okay? So anything that comes here is actually a variable in our programming code. So it doesn't really matter what we put here. Imagine that this is a variable and the program would get the variable's value to input into the string. So it is not really relevant. So let's have a look at the examples. Imagine that we have these 4 strings here. Our objective is to extract a word that is not a variable, and a variable is delimited by a hashtag, an open curly parenthesis, and a closed curly parenthesis. So as you can see in these examples, right? And what we want to extract from the first example is the word the variable 1 is. So 4 words. For the second one would be the variable 2 is. For the third one would be all the words here, the variable is something. And for the last one, the variables are and. So we should skip B and C. Okay? And how can we do that now? Damn. All right. So first of all, we start by what we want to match. As always, start by the base. And what we want to match is actually a word that can contain 1 or more alphanumerics. And we know how to do that. It is a backslash, lowercase w, and a plus sign. So as you can see, it matches any word here. It also matches our variables. Unfortunate. So now we need to make sure that the word we capture doesn't have a follow-up curly bracket and doesn't have a hashtag and opening curly bracket or parentheses before it. Okay. And let's start by the look ahead. Okay. So we need to confirm that there is no curly parentheses ahead of us. And as previously in our previous examples, we already know after doing that how to use lookaheads, positive lookaheads, like masters. And we define it with a question mark and equal sign, and we don't want to use a curly parenthesis. Okay. Oh, that is a positive lookahead. We actually don't want to use it. And to not use it, we need to use question mark and exclamation mark. Okay, nice. And now we move to the before part. As you see, now we are not mentioning the R here, actually, because after R comes the curly parenthesis, bracket, sorry. So now we need to also not match if something comes before our word. And for a negative look behind, we use a question mark, a lower than sign, and an exclamation mark. So the real difference between look aheads and look behinds in syntax is the less than sign. Okay, so what do we not want before our word? We do not want a sequence of hashtags, hashtag, and opening curly bracket. Okay. Well, this regular expression seems quite correct, but as you can see, it is actually matching an A in the variable name. And we do not want to do that. It doesn't match other cases because it only contains 1 letter, okay? And that 1 letter has hashtag and curly parentheses before it and a closing curly parentheses after it. But A doesn't have that. It has a letter before it and a letter behind it. So we don't really want to match that either. And how can we do that? Well, you might think that we could add something like \w here. And now it matches R. Unfortunate. Well, anyways, let's move to a real solution. And we need to rethink what we actually don't want before our non-variable word. And that is a hashtag and an opening curly brackets, but we want a word between them. So we don't want to match just one character of the word between them, right? So what that means, we can fix this issue by adding something to our regular expression. And for example, it would be, we also don't want to match a word character before it. And if we do it this way, it doesn't work because this is an or. For the A case, for this letter A, we don't want to match if there is a curly brackets before it or if there is a letter before it. So what we need to apply is an or operator, or we could actually apply a character class. And if we apply a character class here over hashtag and opening curly bracket and add a \w there, it no longer matches, right? So why doesn't it match? Let's see. So it goes, let's look at our regular expression and apply it to the first example here at the variable part. It goes to the hashtag. It is not a word character, so it moves. Curly bracket is not a word character, it moves. It goes to V. V is a character, a word character, and it checks before it. So there is no word character before it, so it passes, but there is a curly bracket, so it doesn't pass. It goes to A, and now it checks for the word before it, a word character, and it doesn't pass. Oh. And then it goes to R, and it checks for a word character, and it doesn't pass either. So we might think that if we actually remove this, it will work, right? And you wouldn't be wrong. Now, why we should actually apply it? So let's write an example, another one, to trigger this issue. Okay. It continues to match everything we want, as you can see. But now if our variable has spaces in it, it doesn't work, okay? So if we apply this, it doesn't work, it doesn't match what we want. We need to also change our negative lookahead, and we can also apply a character class and tell them that we don't want to match a word there. How cool is that? Now everything that we want is actually matching. This is a tough one. It is not easy to understand, but hopefully you got it. Well, if you write such regular expressions, I will be really proud of you. Next lesson, let's have a look at another tough example. See you there. Welcome back. Are you ready? Let's have a look at another example. So this one is, the goal is to actually match the decimal values of a price for euro currency if the decimal values actually exist and are non-zero or double zero. So let's look at the examples. 1, 2, 3, well, let's say the currency here, I actually forgot. But 1, 2, 3 doesn't have any decimal digits here. 123.0 has a 0, but we do not want to match 0 or double zero. So those two should not be matched. And then we have 123.12. That 12 should be matched because it is a euro currency. And we have 123.13, but in USD, so this one shouldn't match. So in reality, all we want to match is this 12. And we probably could just write something like 12. But let's assume there is a lot of data and you actually want to extract that information. So how we can do that? First of all, let's decide on what we want to match. And we want to match at least one digit, right? And that would be backslash lowercase d and a plus sign. But if you really think about it, the decimals come in only 2 digits, right? So this is usually not a valid representation, but it sometimes is. It really depends. But let's assume for our use case that there could be only 2 digits there, and or none at all, really. So instead of using a plus sign, we actually need to have just 2 digits. And this way we just eliminate the singular 0, but we still keep the double zeros. Anyways, so now we know what we want to match. And let's see what we don't want to match. Or better, how we want to match it. And we only want to match decimals, and the decimals actually come after the dot. So we need to make sure that before our digits here, we actually match a dot. And to do that, we can have a positive look behind. So we can positively assert over a dot before our decimals here. How can we do that? Question mark, less than sign, equals. Positive look behind here. And now we can use a dot. Not that one. No, no, no. You need to escape it because it is a meta character that matches every character. Escape that one. So now, as you can see, we are matching the decimal values, but we are also matching the double zeros and USDs. Well, USD seems easy to remove. We just need to look forward in our text and validate that what comes after our decimals is actually a space and euro currency. So just write a positive look ahead, question mark, equals a space and euro. And now, as you can see, it only matches the decimals for the euro, but it still matches zeros. So this part seems not complete, doesn't seem really complete here. So our look behind and look ahead are working fine, just perfect. We did well. But what we are actually matching is not what we want to match. And let's think about it. We don't want to match a singular 0. Well, that is automatically done by having at least exactly 2 digits. But we also don't want to match double zeros. And what can be done here? So we can have an OR operator. We can actually remove, well, what we could do is just write something, a character class that goes from 1 to 9 and have it twice, right? So it matches what we want. But I actually missed an example here, and a valid example would be something like 0, 7. It is absolutely valid. It can be, so it can start by 0, but after it, a 0 cannot, double zeros cannot exist, basically that. So this solution would work for our initial examples, but look at me, I just added a new one and now it doesn't work. So think ahead, guys. And now let's remove this part and get back to what we had. That is a backslash d and twice of that. And now we can actually use alternation. So why alternation? So that is because we want to match any digits, or we want to match a 0 and then a digit that goes from 1 to 9. So we can write that. Let's write it on the left part of the alternation. So we can match a 0 and then we can have a character class for a character that is 1 up to 9. And look at that, 0 zeros is still matching. That is because it doesn't match the first alternation, but it matches the second one. So because backslash d actually matches 0 and double 0 is totally valid in this case. So we need to alter this one. And instead of using any digit, we can use a character class represented by this, right? And That's it. We've got our valid decimal values for the euro currency. And let's finish off here. Hope you guys liked it. I actually said this one would be a tough one, but looking at the previous example, I think after the previous exercise, there are actually no tough exercises. So go check it out again. All right, cool. I hope you guys enjoyed. Have a good one. All right, welcome back. So let's have a look at the summary and caveats of the third section, which is around lookarounds. And every time you actually hear about lookarounds, you should think that the people who are talking about it are actually talking about look ahead and look behind combined, or maybe just look ahead and or look behind. So it is a generic term to address look aheads and look behinds, all right? And the first caveats we have for lookaround expressions are that first, lookaround expressions are not capturing groups, all right? Even though the syntax that we are going to look in a few seconds at, the syntax has parentheses and it delimits the lookaround, but they do not make it a capturing group, okay? They are also, lookaround expressions are also zero length assertions, and what that means is that they do not match anything, okay? That's what zero length means. And assertion is that they assert, which is the third point. They do not match anything, they just assert over something, okay? And when that assertion is done, the lookaround actually moves back to the point in the text where the assertion started. So for example, your regular expression is being applied over some text, and then we come to the part of the lookaround, and we stop at some part of the text, and the lookaround starts. After the lookaround ends, we go back to that part where we stopped before it started. All right? Next. This is a very important one, and you should be really careful with it. The order of sequential lookarounds is not relevant, but the places where they appear are. So for example, the first example, where the order is not relevant because they are sequential, all right? They are applied at the same place in the text, okay? Because when we apply one assertion, we go back to the same place where we started applying it, okay? So it kind of makes sense that the order doesn't matter because we always start from the same place in the text, correct? So in this example, we actually have a positive look behind for ABC, and then a negative look behind for 1, 2, 3, and then a regular expression that matches the word hello. And here we have a negative look behind for 1, 2, 3, and a positive look behind for ABC, and then hello. It is the same. It will match the same because those assertions, if we're matching against, for example, just the hello string, will start at the beginning of the string, okay? And now the example where the assertions are sequential, but then we separate them. And in this case, the expressions are completely different. So be careful with that. So for example, we have a negative look behind for ABC, then a positive look ahead for hello, and then hello. And it is not the same as negative look behind for ABC, then matching hello, and only then positive look ahead for hello. And that is because, we can move on to here, we will try to match the second one against the text hello. The first one obviously matches, right? It starts before the H, and it looks back, there is no ABC, and there is hello in the front, so it matches hello. Absolutely cool. And in this case, we will start before the H, we look back, and there is no ABC. Nice, this is what we want, right? Now we are matching the word hello. So we actually match the word hello, and we are at the end of the word, after the O. And now we get to our assertion. We want to assert that at this point, in the future, there is a word hello. And this is not the case. There is nothing behind the O. All right, so this expression will not match the text hello. The next one is just syntax, so we don't really forget how to apply our lookarounds. And the only difference between lookaheads and lookbehinds in syntax is that lookbehinds use a less than sign between the question mark and equal sign, or a question mark and exclamation mark. So for a positive lookahead, we use parentheses. Well, we use parentheses to delimit any lookaround, be that lookahead or lookbehind. And inside of it, it should start by a question mark and then an equal sign. And then the regular expression we want to assert and apply to the text, so we can actually assert in the future, okay? For the negative lookahead, we use a question mark and exclamation mark, then the regular expression. For the positive lookbehind, we use a question mark, the less than sign, and then the equal sign, and then the expression we want to use to assert in the past of the text. And for the negative lookbehind, a question mark, less than sign, and exclamation mark. Quite simple. And finally, it is a very, also, well, I always say something is very important, but it really is. I cannot do anything about it. So we talked about that lookarounds are delimited by parentheses, but those parentheses are not a capturing group. But we can make a lookaround be a capturing group by using parentheses just after the initial syntax, so a question mark and, well, in this case, an equal sign for positive lookahead. And then we can use a capturing group here, all right? So it is actually possible to make a lookaround a capturing group, but it is not by default. So in this case, we are asserting over ABC. So we start at the start of the string before the A, and we positively look ahead for ABC, and we assert over it, we find it, and we actually capture it. It still doesn't match anything, okay? We still move back after the assertion to the start of the string. But we now have the ABC in memory, and now we can use that. We can just back reference it by \1 here, and we just match ABC. Now, in this case, we couldn't use \2 for obvious reasons, because we only have just one capturing group. Note that this one is not a capturing group. It is just a delimiter for the lookahead, okay? So that's it. We concluded section 3, an advanced one, and with this knowledge you will be able to write, well, any regular expression you really will need to improve your performance and just really save a lot of time, Hope you do so. Take a look at the quiz. You will really like it, and I hope you pass everything there. Really, you should be doing so. All right, so see you later.
This video is over. Go to starfreelance.eu to download these videos, materials, and sources. Watch more videos to get premium videos and ebooks. We'll be a Starfreelancer.